hydrogen is well known to everyone. Can somebody tell me a few important characteristics of hydrogen? What do you know about hydrogen? You, sir? You know something about hydrogen? Anything? Molecular weight of hydrogen? What? Two. Huh? Two. Okay. So hydrogen is the most abundant element in the universe. Almost 70% of total matter what we have around us is hydrogen. So for sake of simplicity and for you to introduce what we will see in the coming slides, molecular weight of hydrogen is 2.2, as you said. It's very light, almost 7% of air. You could see molecular weight of air is around 29. As I said, most abundant element. So 80% of what we have on Earth is water in ocean, and 218 of ocean is hydrogen. And where this 218 is coming from? You already said yes. 2 is the molecular weight of hydrogen, and 18 is the molecular weight of water. Yeah. Another very good characteristic of hydrogen is very densely packed with energy. So you could see and compare with natural gas, the energy content of LHV. Anybody knows LHV? I want to push the third year. You know what is the sorry? You tried good, but not really. Anyone else? Heating value? LHV, HHV, lower heating value, higher heating value. And what's the difference between LHV and HHV? Maybe on this side. Difference between LHV and HHV? No? Yes?
Water vapor.
Very good. So higher heating value is when you have when you burn something and you do not condense the water. That's LHV. And when you condense the water, take into account condensation of water energy as well. That's your HHV. It's a very light gas. Low boiling point, -252. That means it's very difficult to liquefy it, very difficult to handle and compress it. So where do we use hydrogen? Apart from petroleum refinery, where we use hydrogen in hydrocracker and hydro treater. So normally when you process crude oil, you have a lot of sulfur compounds, and you need to remove sulfur because when you burn these products, you release SOx in the atmosphere. Right? So hydrogen is used in petroleum refining for cleaning these products. We talked about Haber-Bosch process yesterday. We take hydrogen and nitrogen or air and we produce ammonia. Apart from this, there are small uses for you already see here mobility, hydrogen buses are coming up, and some semiconductor industry, methanol production. So that's about uses of hydrogen, how hydrogen is produced. So we'll talk shortly about steam methane reforming. So don't have a look on this one, but I just want to show how it is produced nowadays. So SMR we talked about yesterday, electrolysis is coming up heavily nowadays. But apart from these two main processes, you have several other processes for production of hydrogen. In terms of number, how much we produce yearly? I think this was somewhere around 1960, if I can read correctly, and this is what we have somewhere around 2020. Almost 90 million tons of hydrogen is produced annually. And here you could see two big, let's say, increase. This was 1995 and this was 2005. And this is directly linked to the new standard for diesel and gasoline. Suddenly in 1995, in the European Union there was a new standard specifying the sulfur content of diesel fuel to a very low level, and suddenly all the refineries, they needed hydrogen to clean it up. And then 10 years nothing, suddenly 2005 even stricter standard came in force, and then again they needed hydrogen. So these two sudden increase are associated with these two, let's say, increase in the standards, stricter standards. Country-wise, China is the bigger consumer of hydrogen, almost 22 million ton out of 90. Where do we stand? Almost 6 million ton. Apart from this, other economies like USA, Germany, they are also big producer and consumer of hydrogen. So we saw in previous slides, the main manufacturing process is steam methane reforming, and now electrolysis is also coming up. So now today we'll spend next 1 hour on the SMR process using natural gas. Natural gas is mainly methane, almost 96% we saw yesterday. And as of now, today, almost 75% of hydrogen production is via natural gas, using natural gas. In countries like China, they use a lot of coal, but in India, we have mostly using natural gas. Coal is more used for power production. Electrolysis at the moment 5%, 4-5%, but it's absolutely on rise because of its zero carbon emission. So in process design, if you remember from your courses, does everybody know about onion model? In process design, you normally start with the reactive system, and you go with the separation next level, and then you think about heat integration, and finally whatever heat balance is there, you either cool the remaining heat via utility cooling or so, right? So we'll start with the first step, reactive system, reaction chemistry. So there are three major, let's say, reaction in this SMR process. The first one is steam methane reforming. So CH4 and a lot of steam you put in, it will be converted to CO and hydrogen. Apart from this, there is also a water gas shift reaction where the produced carbon monoxide reacts with the water and produce further hydrogen gas. And combination of these two reactions, we can also say overall a direct reforming reaction is this. So the first one is highly endothermic, the second one is slightly exothermic. And overall you could see the numbers, 206, 41, the overall reaction becomes endothermic. Endothermic reaction means it is required. Now the operating parameters, I will not go into detail the equilibrium constant and all this, but just for the sake of simplicity, here you could see what we want is higher methane conversion, right? And you could see higher the temperature, higher is the conversion. And you will see also different graphs for different pressure. That means lower the pressure, higher is the conversion. That's the characteristics of overall reaction. So another parameter here is the steam and methane ratio. So we are putting, as you saw, methane and steam together, right? So another parameter here is the steam to methane ratio. Right? So higher the steam to methane ratio, higher is the conversion. And you could see also the effect together with the temperature. Now the reaction is also enhanced using catalyst. So once again, I will not go into detail, otherwise we will be spending whole day on this. But this is the space velocity of the catalyst. So weight of catalyst divided by flow rate of the reactants. So more catalyst you put in, more conversion you have, right? But here you could see at certain point the conversion doesn't increase so much, right? And the 3 plots are for different pore sizes, depending on different metal loading on the catalyst, right? So with this graph we know already that that's the amount of catalyst for certain flow rate, this ratio I need, and even if I put further more catalyst, it's not going to help us in conversion, right? So from the plots what we already saw, lower the pressure, higher is the conversion. Now we are already digging into process design. Lower the pressure, higher is the conversion. That means we can use 1 bar operating pressure, right? But problem with lower pressure is also higher volume flow. Right? So can you relate this with your thermodynamic calculation or knowledge? PV equal to nRT, remember? Lower the pressure, higher is the volume. So lower the pressure, operating pressure, higher is the volume flow. And what's the problem with higher volume flow? If you can think about as an engineer, higher the volume flow, bigger is the large vessel is required, large piping is required to have the flow. And with the higher flow rate, if you use smaller piping, what will happen? High pressure drop means higher pumping cost. So if you have lower pressure, high volume flow, either you have to pay for bigger pipe or you have to pay for pumping or compressing. So either capex or opex, capital expenditure or operating expenditure. So once again, lower the pressure. Normally, the natural gas is supplied by a pipeline, and you have certain pressure in your pipeline. So for an example, here you have 20 bar pressure in your natural gas pipeline. So is it wise to select operating pressure below 20 bar? Not really, because you already have 20 bar pressure, and you will let it down to your operating pressure 5 bar, 6 bar. That's not very wise. So generally, operating pressure is also defined by what's the natural gas pressure we have in the pipeline. Right? Then there is another aspect here. So we are producing from natural gas hydrogen. Right? And you will be specifying what's the hydrogen delivery pressure required. So if it's 20 bar, for an example, right? You will not operate below 20 bar. Otherwise, so let's say if you are operating at 5 bar, you are producing hydrogen at maybe 4 bar with 1 bar pressure drop in your plant, and then you have to compress your hydrogen. So sometimes operating pressure is defined by your conditions you are provided with, by natural gas pressure and hydrogen pressure. Then let's talk about the temperature. We saw from the plot, higher the temperature, higher is the conversion. Right? So definitely you will select higher temperature because you want to have higher per pass conversion. But where is the limit? So higher the temperature, we'll see in coming slides, it's an endothermic reaction. That means you have to supply heat for the reaction, but also to heat up the feed from normal temperature up to your operating temperature. Right? I do not have a plot here for CO product, but looking at these reactions, you could see higher the temperature, higher will be your conversion. But conversion means more hydrogen, but also some byproduct, CO, carbon monoxide byproduct. Right? This reaction has opposite characteristics. That means higher the temperature, higher is the conversion of this one, but this reaction, higher the temperature, lower is the conversion. Right? So that means if we select very high temperature, if we select very high temperature, what we'll have? Lot of CO byproduct, right? Another problem with high temperature, very high temperature is, if we have very high temperature, operating temperature, we have very high heat demand. Heat of the feed to reaction temperature. So just for sake of simplicity, I can mention here, optimum is somewhere around 850 degrees. At this temperature, we'll have very low unconverted methane. That means we have very high conversion, right? And very low CO byproduct. And that's our target. That's what we want to have. So we talked about two parameters: pressure, temperature. Another important one is steam to feed ratio, steam to methane ratio. You could imagine if we have high steam to feed ratio, means if we are supplying excess steam for the reaction, high will be the conversion and low will be the CO product. But problem with having high steam to feed ratio is, if we have more steam than required, we have to heat up the steam. So additional heat is required, so more energy consumption. Right? So once again, as I mentioned, optimum for pressure 27, temperature somewhere around 850. Similarly, for steam to carbon ratio or feed ratio, optimum is somewhere around 3. Stoichiometrically, somewhere around 2.5 we need, and we supply a little bit excess S3. Catalyst we already saw, space velocity, we saw from the plot, that's a certain ratio of catalyst amount versus feed flow rate. So optimum is somewhere around 100 grams per mole per hour of feed rate. So now we already set the optimal operating temperatures or conditions for the reaction system, reactive system. So that's the onion model of process design I was talking about. You guys are familiar. So we start with the reactor system, and we already saw that we do not have full conversion of methane. That means we have some unconverted methane. On top we have some byproducts like carbon monoxide here. Since we supplied excess steam, and we also have unreacted steam there. So what comes out from this reactor or reactive system would be hydrogen, unconverted methane, CO, water or steam, and any other byproduct. Then we look into the heat balance. We already talked about the temperature. We have to supply heat to bring it from feed temperature to the operating temperature. Where are the heat available, waste heat available? So we are talking about 850 as operating temperature. That means the product stream is at 850. What do? We do not supply hydrogen at 850 degrees. And then finally we will see if we have some heat left in the product stream. So what to do with this heat? Okay, so earlier we already fixed the reaction temperature. We selected as 850. How do we supply heat at such a high temperature? So what are the heat transfer modes you guys are familiar? Sorry, please. Yes?
Conduction, convection.
Conduction, convection and radiation, right? And what are the heat transfer medium normally we use to supply heat? Somebody said steam, huh? Steam. And steam can supply heat or energy up to what temperature? Sorry? Maybe up to 300, 400 degree, because at 300 degrees steam pressure is almost 100 bar. So at this high temperature, the only way to transfer heat is via radiation. You burn something and via flame you transfer heat. And can somebody tell me what's the name of this equation? Or maybe the constant? Boltzmann constant, exactly. So here the heat transfer rate is directly proportional to 4th power of the temperature of two bodies. Difference in temperature of two bodies of 4th power. Okay, so we already know we supply natural gas and steam, and we already know we are using catalysts at certain space velocity. So normally you take natural gas, burn it, that will create a flame temperature of somewhere around 1800-1900 degrees, and that's good enough to supply heat from the combustion gases to the gases flowing inside the tube. So what happens in the starting, your gases are at 1900 degree, right? And your feed is at, for now we can say 35 degree, ambient temperature, let's say. And you will have very high heat transfer rates in the starting, but as you go along the tube length, what will happen? Your flue gas will get cooler and cooler because it's supplying heat to your feed stream, right? And your feed stream will start getting hotter and hotter. At certain temperature, reaction will start, right? And it will start to absorb more heat because we already said it's an endothermic reaction, so a lot of heat is required for the reaction, right? So what it means, ideally or theoretically, I can put a very long tube, right? And cool the gases, the flue gases or the combustion products up to certain temperature, up to 850 degree, right? But what will happen, we saw from this reaction, this equation, that your heat transfer rate is proportional to, or Q by A is proportional to 4th power of T, difference of hot and cold side, right? So once we go along the tube length, your flue gas is cooling down, and slowly your heat transfer rate is also coming down and down. That means you will need a lot of heat transfer area, right? So in the starting, first 1 meter or 2 meter of tube, you will have 70-80% of heat transfer. To have the same heat transfer, you will need maybe 10 times more. So there is an optimum length of the tube, or in other words, there is an optimum flue gas outlet temperature. So you can cool the flue gas maybe up to 1100, 1000 degree, but below this, the heat transfer rate, because the difference, 1000 degree and 850 degree, that's too low, that you need a lot of heat transfer area, and it's not economical. So last two lines, you could imagine yourself, in the starting you have a very big flame. So generally this flame is 2 meter, 2.5 meter long, right? So first few meter of the tube length, you have very high radiative heat transfer, but as you go below the tube length, the majority of heat transfer is taking place via convection, convective heat transfer, right? So flue gas is flowing this way, feed is going in the tube this way, and the last end of the tube, I actually, to fit in this, on this slide, I just cut it here, but as you go along the tube length, here, majority of heat transfer is via convective, and on top reason it's via radiative heat transfer. So from this, now we'll start preparing block flow diagram, or the process flow diagram. No? That's the next part of the process design. So you already saw the reactions, right? We said there will be some unconverted methane, so that's here, up to 3%. Since we supplied a lot of steam, excess than what is required, so that unconverted steam or unreacted steam is coming here. 45% is our main product, which is hydrogen. You also have byproduct CO, carbon monoxide, and an unwanted product, which is CO2. So once again, for sake of simplicity, we will not go into detailed calculation. We'll need another 2-3 hours for that. But that's the typical composition of the product gas, what comes out on the product gas pipe. Now if you apply a simple heat balance between across this reactor system. So the heat out would be, everybody is familiar with this equation, I'm pretty sure, right? Heat transfer forces, you already had it. So mass flow rate of feed, specific heat of your feed, but from inlet to outlet, your feed is converted to product gas. So CP is not only the specific heat of feed, but it's also the specific heat of your product. So somewhere we take the average of feed and product, that's the specific heat, and the temperature difference. So for now, we assume that we do not have any preheating of natural gas. So natural gas is coming at 30-35 degree. We have to heat it up to 850 degree, and we have to supply the endothermic. Sorry for this mistake. This reaction endothermic heat actually. And heat in will be the natural gas fuel. So that's natural gas. The same feed what we are tapping out some as fuel. And for combustion you also need air. So that's the air, combustion air. So that's heat out and heat in, right? We already saw the optimum temperature, right? But in terms of fuel, you could imagine higher the feed temperature, higher will be the fuel consumption, right? And higher the efficiency. With efficiency, I meant what's the flue gas outlet temperature? So when we burn natural gas, temperature here is somewhere 1900 degree, and we said after the reactor system, the flue gas temperature is somewhere around 1000 degree. That means, can somebody say what's the efficiency? Thermal efficiency? 1900 to 1000. So theoretically you can recover heat from 1900 degree up to maybe 40 degree or 30 degree, right? Because your combustion feed was at 30 degree, and you are recovering heat only to 1000. So 1900 minus 1000 divided by 1900, somewhere around 50 degree, 50%, right? So that's the efficiency what we mentioned here. So higher the efficiency, that means if we go lower with the temperature, instead of 1000, if we cool the flue gas to 950, our efficiency will slightly go up. But the downside is you have to pay more for the tube area or the heat transfer area. So it's once again a trade-off between optimization between CapEx and OpEx. If you want to burn less fuel, you have to put in more heat transfer area, which is nothing but CapEx. And only on the combustion side, if you put similar heat balance, so what comes in is natural gas fuel at 30 degree. What combustion air comes in at 30 degree also. What comes out is the flue gas at 1900 degree. And what goes out is the flue gas at 1900 degree. And what else comes in is the LHV of your fuel, right? So that means if I increase the temperature of air, my heat in is increased, right? So if I have hotter air going into the furnace, I will also need less fuel, right? So that's basically a little bit about optimization, trade-off between CapEx, OpEx across the fuel system. We go back to this onion model. We had this reactor system. Separation will come further because we have very hot product stream. So we will first look into the heat recovery system, H part of this model. Now we already seen product stream is at 850 degrees. So you have to supply hydrogen product at ambient temperature, which is maybe 30 degrees. So there is a lot of waste heat in the formed gas or the product gas. We can cool the gas from 850 to 30 degree and recover this heat and use it somewhere within the process, right? So we already saw that heating air and feed will reduce fuel. So heating air reduce fuel is what we saw here. And heating feed will also reduce the fuel requirement. That's what we saw here from this MCPTT. So the reaction temperature is 850. If we supply or if we feed the natural gas at high temperature, definitely the heat requirement in the furnace or the reactor will be much lower, right? So what we see here is we have a hot product stream where we can recover heat, and we also have some cold feed stream where if we supply heat, we'll have less operating costs because of less natural gas, right? So what we can do, we can cool the reformed gas and supply heat to natural gas and air, right? So that's typical heat integration, right? Now, what happens? So we said we will cool the reformed gas from 850 degree to 30 degree. Right? That means somewhere, whatever heat transfer equipment you will use, you will have somewhere the metal temperature between 850 degree and 30 degree, right? And especially with this kind of product composition, there is a phenomena called metal dusting corrosion. What happens is this Woodward reaction, where if you have very high partial pressure of carbon monoxide, it will get converted to carbon dioxide and elemental carbon, right? And what's the problem with this elemental carbon? It can go into your metal structure and it will form metal carbide. That's a form of corrosion. So what we see in all the rust, similar metal carbides you will see. And once it starts, it gets very fast corroded. That means you can have leaks, hot spots, which needs to be avoided. What it means, that we have to have the temperature of your equipment handling this composition of the gas, never in the range where this metal dusting corrosion is very high. And typically, it's very severe between 400 and 750 degrees centigrade. So that means somehow I have to cool the gas from 850 degree to whatever temperature without seeing the metal temperature in this range. Can somebody think about how we can do that? Can you think about cooling a gas suddenly? Sorry? Sudden expansion. Quenching? Somebody knows about quenching? Huh? Quenching, yeah. So what you can do, you simply add water, liquid water, and it will absorb a lot of heat from your gas, and your metal will not see this temperature, right? But what's the downside of quenching? You will cool the gas directly from 850 degree to maybe 150 degree, and all the heat is lost in quenching in water, evaporating water. So you can do quenching and avoid metal dusting, but you will lose all the heat. Suddenly your heat was at 850 degree, very high grade, very high value heat, and you are now converting this to a low grade heat, which is somewhere around 300 degree. So if we avoid, let's say this 400 degree, we want to avoid, we'll simply put water and create a gas from 850 to maybe 300 degrees. But with this, what we are doing, we are degrading the value of heat, degrading the heat what we have in the gas. Yeah, that's another repetition of what we saw here. Earlier, the severity of this metal dusting corrosion is somewhere around 450, 750 degrees. Right? As we said, there is one option is to quench the gas, right? But with this, we lose lose a lot of energy and we degrade our available waste heat, right? Another difficulty is once you add water, you are adding lot of water, you have to remove it all. So your separation system will also become expensive. But fortunately, there is another way. Heat transfer coefficient, individual, overall, the heat transfer courses you already had. Right? So in convective heat transfer, you know, if you have gas flowing on one side and water boiling on another side, so there is a huge difference in heat transfer coefficient. So the gas side heat transfer coefficient is very low, but if you have boiling surface on another side, heat transfer coefficient is high. What it means? Are you familiar with this temperature profile with film on the hot side, film on the cold side? The temperature drops from bulb to film and across the film. You guys familiar with this?
Yes.
So it's such a combination. For example, if you have this gas being cooled from 850 to maybe 300 degree, right? And if you have boiling water on the other side, where will be the major temperature drop across hot side to the cold side? Where will the biggest temperature drop? Where the heat transfer coefficient is high or low? No? So the major temperature drop will be where the heat transfer coefficient is low. Heat transfer coefficient is low means that resistance for heat transfer is high, because resistance is inverse of the heat transfer coefficient, right? So where on the gas side you have very low heat transfer coefficient, your resistance is very high. So the temperature drop, major temperature drop will be on the gas side film, and there will be small temperature drop across the water side film, because it's boiling surface on this side. That means instead of quenching, if we start producing steam using this reformed gas or product gas, high carbon monoxide, and in the heat transfer equipment, we will not see the metal temperature above 300, 400 degrees, right? So for example, if we are generating 220 degrees steam here, right? And the temperature drop across the water side is very low, maybe let's say 10 degrees. And on the metal surface another 10 degree, my metal on this side will be 260 degrees, right? So that's the way you could cool the gas, and your metal will never see temperatures above 300 degrees. So that's an intelligent way compared to just quenching the gas. Yeah, that's again the repetition. So your reformed gas coming in here, right? Your metal tubes are always cooled with water. With this you can avoid your any metal surface with this coming in contact with this high partial pressure, CO, temperature, anything above 300 degrees centigrade. So what we are doing here is slowly building this block flow diagram. So first we only had the feed stream coming in, the steam coming in here, right? To produce reformed gas. Now we add another block, which is the boiler, and we already know that we need steam for our reaction. Right? So what we are doing with this new equipment or new block is generating steam and also cooling the gas, right? And also recovering heat. So once we have this steam needed for your reaction need to be generated as well. That needs also energy. So if you can generate within your process, you're already reducing your operating cost, right? So in this one we cool the gas from 850 to 360 degree. As you said, we already generate steam which can be used in the process. Now 360 degrees still a lot of energy left in the gas. Right? What we can do further cool this gas and preheat the feed and air. So another step in heat integration. But we saw the composition of reformed gas. We have some byproduct carbon monoxide, right? And we already talked about this, that the SMR reactions, they are optimally, they have optimum conversion at 850 degree, but the water gas shift reaction, it has optimum temperature, operating temperature of somewhere around 350 or 400, right? That means if we use a certain catalyst, which that means if we use a specific catalyst, we can have this reaction. So we add another step, and we carry out this reaction to further convert whatever byproduct we had produced from the first step, and enhance our hydrogen production. Right? So we add another block here, the shift reactor, where, as we saw already earlier, the SMR reaction is highly endothermic, but the water gas shift reaction is exothermic, right? It means here the temperature increases from 360 to 420, and you already see we convert whatever carbon monoxide we had, and we reduce its composition from 4% to less than 1%. Right? What happens with this? We also increase our hydrogen yield or production. Right? We can even add another step, which is called low temperature shift. So this is medium temperature shift, somewhere around 300 degrees centigrade. We already talked about this. The lower the temperature, higher is the conversion of this shift reaction. We can go even further with the temperature. We cannot have the same. So lower the temperature, higher is the conversion for this water gas shift reaction. But you see, it's exothermic. So as the conversion increases, temperature also increases. So both are going in opposite direction. Right? So what people generally do, if they need very high purity hydrogen and fuel is very expensive, what they normally do, add another step and even bring this carbon monoxide composition from 1% to 1%. But they need to cool the gas from 420 to maybe 250, and then add another low temperature step. So far we talked about the R of the onion model, right? And H of the onion model. We saw even after adding this shift, let's say step, we still have a lot of byproducts, unconverted reactants in our process. So now comes the separation of this onion model. What kind of separation methods we can use if we have to purify the gas stream? Sorry? Somebody said membrane, right? Oh, yes, yes. PSA system. PSA system. And what's the PSA? Pressure swing absorption. So absorption is a phenomena of molecules passing through certain structures, certain pore sizes. It also depends on the absorption forces. And fortunately, hydrogen being the lightest, smallest, very low atomic diameter, molecular diameter, it's very easy to separate hydrogen from other gases using this method. So if you have let's say molecular sieve, some absorbent material, if you pass through this bed, our product gas, hydrogen will not be absorbed on this way, and other gases will be absorbed. So that means, for example, let's say that's the bed we have gas coming in, or let's take this example. It's a bed of adsorbents. We pass through our product gas, which has almost 50% hydrogen and other byproducts, right? Through this bed, what will come out here is pure hydrogen, right? But your bed will not last for days or months or whatever, because you are absorbing other gases on your absorbing material. Right? So at certain point, you will not have any space, any pores which can absorb any more gases. Right? What you have to do, once again, a trade-off between operating cost and capital cost. If you make your vessel very big, you can absorb for a longer period of time. Right? But if you make it smaller, within minutes this bed is already charged with your byproduct gases, right? So normally optimum size of these beds are somewhere around 12 meter, 13 meter height, 3 meter diameter, and they get saturated within not days, hours, within minutes, right? What it means, you need to have at least 2 beds. So one will be absorbing the gas, and at the same time, once this bed is absorbed, the second bed will be dissolving. And this phenomenon, you could imagine, absorption is higher at higher pressure. So if you have high pressure, you can have more absorption. If you have high temperature, you will have less absorption. So we want to have higher pressure during absorption, and we want to have lower pressure during desorption. That's why the name came from PSA, pressure swing absorption. So you swing the pressure, you absorb at higher pressure, right? Once this is saturated, you simply release the pressure, so gases are removed. But not all the pores are free from the gases, so there is a absorption as well. Even at lower pressures, you will not dissolve all the gases. So what you can do, either increase the temperature of this bed, comes the temperature swing, you have to increase and decrease the temperature, or what you can do is you can pass through pure hydrogen gas or a smooth gas. So whatever, remove the remaining adsorbed impurities, right? So minimum you need two beds, right? But to have continuous supply of hydrogen, you will need in reality more than 2 beds, because the absorption and desorption times are not same. You can work with 2 beds if you have absorption and desorption time of similar magnitude, right? But normally absorption is, let's say, somewhere around 1 minute, and desorption somewhere around 4 minutes. So that's why you will have more than 2 beds, because of this difference in absorption and desorption time. So these absorption materials or absorbents, they operate optimally at somewhere around 35 degrees. What it means, we cool our gas so far from 850 to 360, then we went to shift, temperature increased because of the exothermic nature of the reaction to 420. It means we need to cool the gas from 420 to 35 degrees. So what we do after shift, we work somewhere around 420. At the PSA inlet, we need to have 35. It means we do cooling here, and we can supply this heat to preheat the gas from 30 degree to 360 degree. What we did with this heat integration, recovered heat from the waste heat product gas before PSA, which was also a requirement for PSA, and thereby increasing temperature of feed gas, which helped us in reducing the fuel consumption, right? Because heat load on the reformer is, or the furnace is reduced. Right? Now, the gas will be cooled somewhere to, not from 420 to 30 degree, but in reality up to 150 to 160 degree, right? And you already satisfied all the heat requirement here, right? For the feed. So the remaining heat, what will be left, will be just rejected to atmosphere. Why? cooling water and air cooling. Right? So that's the U part of your overall onion process or process design. So we already looked at the heat recovery on the process side, the product gas, but we saw that our flue gas is also at 1000 degree. And there's a lot of waste heat available in flue gas. We saw that economically we selected 1000 degree based on capex opex. Higher the temperature, bigger this temperature is, lower is the heat transfer area required, but on the other side we need more fuel. Flue gas, normally we can recover heat from 1000 degree to 150 degree. Do we have any consumer or any other process stream which need heat? So we heated the gas up to 360 degree so far. Right? We saw it here, right? And where this 360 degree came from? Because we have the hot stream at 420 degree, right? So we cannot heat our feed gas above 420 actually. But there is a optimum temperature approach. Temperature difference between hot stream and cold stream. So in this case, it's somewhere around 60 degree. So we can heat the stream up to 360 degree because our product gas is at 420 degree, right? But what we can do, we can heat it further to 650 or even higher using hot flue gases. We already know, we repeated that several times, that higher the feed temperature, lower is the fuel consumption, because heat demand is low. So we heat the gases from 360 to 650 using flue gas. We can generate further steam because we saw so far we are not generating enough steam within the process. We do generate in this boiler, but we still have some steam requirement from external sources. Right? So flue gas can be used to generate steam, right? And we can also preheat the air. We already talked about it. What are the air temperature, lower is the fuel demand. So further optimizing it, what we can do, we can preheat the air also from 30 to 450. Now if you look at the temperatures here, it's 450. So gas is being cooled from, let's say if I have a plot here, 1000 to 150 degree, and we have a temperature cross somewhere here, air is to 450 and the steam is generated and superheated to 350. So it's better to split the air preheating into two steps to have optimum use of your heat. What we do, we split the air preheating into two steps. First, increase the temperature from 30 to 250, then generate steam, and then this 250 air, what comes out here, goes in here, comes out at 450. So what we are doing here is having a regular temperature profile. You could see here, so 30 degree, 250 degree, another stream 350, then 450, and then 600. So you always use your heat at the optimum temperatures. Right? So that's how the overall block flow diagram looks like. We have natural gas coming at 30 degree. We preheat it to 360 using product gas. Further to 650 using flue gas. 650 degree natural gas together with steam goes to the reactor. Right? And when we talked about steam generation here, when we had steam generated here, we had steam requirement from external sources. But once we started to generate steam here, suddenly we have excess steam generated, more than required in the reactor system. And that's why our block diagram now changed from this side to this side, from this side to this side, right? So we had this R reactive system here, H heat integration on here, separation here, and final cooling from 150 to 30 degrees, that's utility U here. So that's how we complete our one-year model for the process design. And that's how the overall block flow diagram looks like. So this is just the block diagram just to show how the flows are here and there, but in reality it looks something like this. You have the natural gas coming in. You need some pre-treatment, which I skip just for the sake of simplicity. And that's how your furnace looks like. You have the natural gas fuel together with air, burn, catalyst filled in the tubes, feed stream coming in here. You could see natural gas coming in, preheated, pre-treatment, further preheated, and then entering the tubes at 650. Hot gas coming out 850. Steam generation here. That's the steam drum, the shift, what we also saw in our block diagram. Further cooling, preheating the feed, right? And final cooling, PSA system, and then you have your hydrogen product. Right? Questions so far? Interesting? Not interesting? Sorry?
CO and CO2.
So what happened? What happened? Yeah, good question.
Monoxide.
Yeah, carbon monoxide. Good question. So what happens is you separate your pure hydrogen here, and generally you have 90% recovery of your hydrogen, because we saw during the desorption step, you need pure hydrogen to remove your gases which are absorbed, right? So you will have somewhere around 89-90% recovery here, and all the CO, CO2, a little bit of water, they all ended up here in this tail gas. This is called tail gas. So during the desorption step, we supply hydrogen. First of all, it's depressurized, right? You don't supply any sweep gas. The gases are dissolved automatically, and all these components are ended up all are in this stream, right? Since this stream contains a lot of carbon monoxide, some unconverted methane, some hydrogen as well, because we use sweep gas, pure hydrogen as sweep gas, it has some fuel value. So what we do, we use this as fuel. So here you could see natural gas with feed, and this was a fuel stream. And if we have this byproduct stream which has some fuel value, we add this with the fuel. So they all this CO, remaining CH4, hydrogen, they all are burned in the furnace and end up here in this process. That was a question, huh?
And what if we use pyrolysis instead of reforming? Because we don't have any carbon byproducts in this. Carbon dioxide monoxide byproducts.
Yes, that's a new, we'll see in the next presentation what are other methods of producing hydrogen. So pyrolysis is one. It's still very in very early stages. We'll see in detail on this process. So far we talked about the process design, the temperatures, heating condition, and heat integration, right? Separation. So that's all the technical stuff. Now we go from process design to a little bit on economics. So once again, just for sake of simplicity, I already put the specific natural gas requirement somewhere around 13 to 15 megajoule per normative cube for the hydrogen. Right. Now if you consider natural gas price somewhere around 30 euro per megawatt hour, if you do a simple maths, that's in euros per megajoule, right? That ends up at 1.16 euros per kg of hydrogen. Within your plant, you don't use only natural gas. Here you see in the block flow diagram, basically you are using natural gas and some electricity, generating hydrogen product. We already talked about this. We have excess steam production, so we can sell this steam also. So we don't see here, we are generating steam. When we generate steam, we also have some blowdowns, some make up them water requirement. So there are some other operating expenses. It's not just natural gas, but natural gas is the major operating expense in a SMR process, right? So let's assume, once again, sake of simplicity, 10% for other OPEX. We end up at 1.36. But to do all this stuff, we also need to buy and install this plant. Capital expenditure. Once again, let's simplify it. 15% of your total cost is for capex, and remaining 85 for opex. Means hydrogen price somewhere around 1.5 euro per kg. I think that's, if you convert it into rupees, that's a similar price is what we have here in India using SMR process. So we slightly talked about this steam co-production. So let's look at it in a little bit detail. So operating parameters we already defined, and what we define for this example, we end up with steam co-production, right? So high reforming T or reaction temperature, that means we need to fire more, burn more fuel. What it means, we have more waste heat in the flue gas and more steam co-production. Similarly, high reaction temperature, more heat in the process side. Right? The forming temperature is high, that means product gases are not at 850, it's 950, and in the boiler you generate more steam. Once again, but the other side, so first two are towards more steam production, right? But if you have higher temperature, we also have higher conversion. Right? Higher conversion means we'll have less throughput for the same amount of hydrogen production, and we'll have less steam. Also, high temperature, reaction temperature, more conversion, less process and waste process side flow, because for the same hydrogen throughput, you also need less feed, right? So the flows are also lower. It means once again less steam. Another parameter, high steam to feed ratio, that means more conversion. More conversion means less wasted in the process, once again less steam. But on the other side, if you have higher steam to carbon ratio, what will happen? You have to fire more because you are flowing to the whole plant a lot of additional steam. That will generate more steam. So higher steam to feed ratio has two effects, and both of these two effects are in the opposite direction. So one will have less steam, one will have higher steam. So what I want to say here on this slide is, it's a complex, complicated combination of different parameters, and for optimization, you need to select best combination of all this. Right? But the air preheat has only in one direction. Higher the air preheat temperature, less waste heat in the flue gas and less steam. And this high air preheat temperature will have biggest effect on your steam co-production, because we saw in this waste heat recovery part, if you preheat your air higher, you will generate less steam because you have same amount of energy left in your flue gas. So if you increase these two, this one will go down. So air preheat temperature has the biggest effect on the steam co-production. We said already that with these parameters we produce steam as byproduct, right? And you can sell this steam. And how do you value your steam? So we already said natural gas price somewhere around 30 euro per megawatt hour, and LHV of natural gas, for example, is now 47, right? So natural gas value in megajoule. And let's assume we are generating steam at 40 bar, superheating it to 350 degree. That has a heat enthalpy of somewhere around 3,200 kilojoule per kg or megajoule per ton. So if we assign 1-to-1 value in natural gas to steam, your steam price would be 27 euros per ton, right? But we know there is a efficiency of natural gas to steam conversion, right? Somewhere around 90%. The steam price will be 30 euro per ton. Right? And once again, we saw from previous slide, for capex simplicity, we assume, let's say, 10% here, 10% of your total cost is capex. So my steam price will be 33 euro per ton for assuming 1-to-1 value, right? And generally, so we co-produce steam with hydrogen, right? And how much it is? Generally, for these parameters, what we selected is somewhere around 0.3 kg steam per 1 meter cube of hydrogen. And if you convert non-meter cube to kilojoule, you end up with 3.3 kg steam per kg hydrogen. What we are trying to do here is establishing 1.5 euro per kg was our hydrogen price. How much money we can get from steam and reduce our production cost of hydrogen. Now we assume in the previous slide the steam value as 1-to-1, but it rarely happens that you get the same value of your steam. Generally, steam value is somewhere between 30% to 120%. You never get full value of your steam or the energy content what you have in your steam. So generally you get less than 100%, but at some locations where imagine you have a plant, your plant, and they suddenly need some steam, right? They don't want to install a boiler or a steam generation system within their limits or within their plant, and they come to you and say, you have some excess steam, can you supply steam to us? And there, in such scenarios, you can have a little bit higher value of your steam, but it rarely happens. It's always less than 100%. So if I translate 3.3, right, it becomes 10 euro to 40 euro per ton of steam. So we saw in the previous slide is if for 1-to-1 it's somewhere around 33 euro per ton, but if I get only 30%, it's only 10 euro per ton of steam. So my hydrogen price will go down either from 0.03 or 0.13, so 1.5 reduced to 1.47 or 1.37. So as I said earlier, optimization of operating parameters is really based on client's cost data. What's the natural gas price? What's the hydrogen price they will pay? And what are the cost of utility? So far we talked about this reactor system only, reactor tubes, but that's how it looks generally, somewhere around 18 meter high. You will have tubes here somewhere around 12 meter. So there are different design of these reformers, but most of them have tube length somewhere around 12 meter. And you supply the feed stream from top. Most of these systems are top fire, means you are firing from top. Feed also comes from top. Catalyst is generally catalyst, nickel base, loaded on aluminum oxide. There are several licensors for designing such plants. So apart from steam methane reforming, you can also have partial oxidation. It will also generate syngas, but partial oxidation generally has higher operating temperature. That means your CO content is high. So SMR is best suited for pure hydrogen production, but in many cases you need combination of CO and H2. One example is methanol. So methanol production you need carbon monoxide and hydrogen in a certain ratio. Then you sometimes supply SMR and ATR combination or POX. So there are several other methods of producing hydrogen. But today we'll limit our discussion only on the SMR. Yeah, with this I rest my case. You all were yesterday here, na? So ये सब enter वाली. So we talked about climate change, greenhouse gases, and all those things yesterday. Slightly touched upon hydrogen. And this morning we had a look on conventional hydrogen production process by steam methane reforming. But today we'll move from conventional method, which is very carbon intensive, hydrogen production, to cleaner hydrogen production. So we'll look at the different colors of hydrogen. Probably you might have already heard about grey hydrogen, brown hydrogen, blue hydrogen, pink hydrogen, yellow. There are so many colors, so we'll talk about those things. We'll look at the economics, going from brown to green. So how the capex and opex change from, if you go from brown to green. We talked about the energy transition yesterday, how the electricity production is moving from carbon intensive sources to renewable power, transportation. We also looked at some industrial applications, right? And we found that some of the industries are really hard to abate. Means we cannot replace the energy sources that we are using at the moment. So we'll look at the hydrogen, which is also a hard to abate industry, how we can use hydrogen there. We already saw yesterday there is a price gap between dirty and clean. How the government policies are on the hydrogen side, right? And then finally, energy carriers, which can carry this hydrogen from one location to other location. So to start with the different colors of hydrogen, so probably green, blue, and grey is more familiar, but they have even more colors here. So purple, pink, which is, let's say, electrolysis hydrogen production, but the energy supplied is via nuclear. So it's basically there are three: grey, conventional source, which is natural gas, and blue. Blue means you produce grey hydrogen, but then capture the carbon dioxide and sequester it somewhere or utilize it somewhere. That's blue. And green is absolutely using no fossil fuels, so purely based on electrolysis. So you use renewable power or green power to generate hydrogen. Right? So that's basically here. And you could imagine greenhouse gases footprint, CO2 footprint for the green hydrogen will be almost zero. Also for the nuclear, really zero. We also have another color, yellow, which is something between green and blue, or maybe blue and grey. That means you are using hydrogen production via electrolysis, but the electricity you are using is not purely green electricity. So you are still emitting CO2 somewhere else. So the CO2 footprint theoretically for green hydrogen will be zero. For nuclear also theoretically is zero, because we are not using any carbon intensive fuel. For yellow it's little bit more than zero. Talking about blue hydrogen, so whatever we'll see in coming slides, how much the CO2 footprint or how much CO2 we emit per ton of hydrogen production. And we said blue is the one where we capture all this carbon dioxide. But there is a limit, you cannot capture because of the equilibrium of every process. So economically, you can capture up to 90-95%. Nowadays even higher, but up to 95-96 is optimum. So you will still have some CO2 emissions, right? So a little bit higher for blue hydrogen than yellow. So that's the order of, let's say, increase of CO2 footprint. Then there was another one, turquoise hydrogen. I think we talked about, you know, a little bit of this. So basically this is the pyrolysis method, where you simply heat up the methane gas at very high temperature and crack your methane between carbon and hydrogen, elemental carbon and hydrogen gas. Somehow similar to grey hydrogen, where you have natural gas and you kind of crack it between, but unfortunately it's cracked between CO2 and hydrogen. And in this case it's purely carbon. The advantage of pyrolysis is the energy requirement is much lower, because direct cracking of methane is not that endothermic. Although temperature requirement is high, but the reaction heat is much lower. So in a Samar process, we saw this morning, unfortunately some of you were not here, the hydrogen process, you have CO2 emission because you are burning natural gas as fuel, but we saw from the PSA process, the tail gas, carbon monoxide, CO2 and unreacted methane, that also goes to the fuel system. So out of every 10 kg of CO2 we release for the grey hydrogen, 3 or 4 kg comes from the fuel system. Right? And if you have a reaction process where your endothermic reaction heat is much lower and you need much lower fuel. So comparing grey hydrogen and turquoise hydrogen, in turquoise one you will have much lower, 20-30% lower CO2 emission. Now you can make the turquoise and blue mix together, or you have turquoise hydrogen and you either use this carbon, elemental carbon, finds its application, alumina industry where you have electrodes, some other application where you can use this graphite particles. Right? But wherever you use it, finally it will end up as CO2. Because these graphites, after 10 years, 20 years of use, will be burned somewhere. So that's not the ultimate solution. So blue hydrogen you see as capture and sequester somewhere in geological formation for maybe thousands of years. That's considered a permanent sequestration or fix, but not in the turquoise form. So grey we already talked about based on natural gas. We spent almost 1.5 hours this morning looking into details of the process. And brown and black is nothing but using coal, different kind of. So this morning, yes.
Production of hydrogen through biomass. Biomass pyrolysis or gasification would be as turquoise.
I think biomass gasification without carbon capture would be somewhere similar to blue one. That means because we are releasing CO2, but CO2 is coming from biomass, and we consider that this biomass is generated from CO2 coming from the atmosphere. So CO2 footprint wise, if we have hydrogen production without carbon capture using biomass, it will be somewhere close to blue hydrogen. And if you have biomass as your feedstock and produce hydrogen gas via gasification or whatever, and capture the CO2 and sequester it somewhere, you will have negative emissions, so negative CO2 footprint. So it will be even better than green hydrogen. That's what people are talking about, thinking about this. Because biomass use, you consider it as CO2 coming from atmosphere. So, like for natural gas, the CO2 you have to take into account. But when we do the CO2 footprint for biomass gasification based hydrogen production, we take zero CO2 carbon coming in the system, because this is from the biomass, and biomass is nothing but atmospheric CO2. So this morning, as I said, we talked in detail about the conventional process using methane, and the green one, blue we already talked about. It's nothing but the conventional process with CO2 capture, and the most, let's say, on the other extreme is electrolysis based hydrogen production. Right? Within electrolysis also there are, let's say, two major technologies available: alkaline electrolysis and PEM. Electrolyte membrane. So this is an established technology. I think in the chloralkali industry they use it for many years, where hydrogen is a byproduct, chlorine industry. So they are making use of this technology now to go from chlorine production to hydrogen production. Right? Very well established. There are a lot of licensors, suppliers provide this such electrolyzers. So since it's already for many years existing, scale is very high, that's why the cost is already down, so somewhere around 1,000 euro per kilowatt. The PEM is the new one, latest one. It's already industrialized. Many electrolyzer-based plants are coming up with this technology. Cost is a little bit high, it's still high because it's very new. Advantage-wise, between alkaline and PEM, you'll have relatively long startup times for this one. This can start very fast. Another comparison or disadvantage between these two is the efficiency of this one was slightly lower, somewhere around 65%. So when we say efficiency here, in terms of energy, whatever kilowatt hour we put in as electricity, only 65% will come out as hydrogen, as energy. So this one is somewhere around 65, 66. This is already touching 70%, so a little bit higher efficiency. There's another aspect between these two. So when we say efficiency is 65% at start, or let's say when your electrolyzer or cell is new. But with the time, your efficiency starts dropping. For example, in solar PVs also, they guarantee for 20 years, but a certain efficiency, that 90% efficiency is guaranteed for the next 20 years. So efficiency drop for alkaline is also high for the same period of time. So this one is really picking up fast, and future will be dominated by PEM. Then there is another one at somewhere between lab to industrial scale, which is a solid oxide electrolyzer. Efficiency is very high. Just to go to basics once again, between both of these technologies use pure water, or purified water, demineralized. And difference between these two and this one is, this one uses steam. So once again, the heat balance we talk about, we are supplying water, and then we are taking out hydrogen gas. Right? But if you can supply water as steam, you are already putting more energy inside the system. So efficiencies are as high as 80%. Right? So it's very efficient, but as I said, still somewhere between lab scale and industrial scale. So a little bit higher scale, people are already building up. Some are already operating demonstration scale plants. But if this one hits the market, and if we have higher efficiency, 80-85%, that will be very good, because you could see 20% rise from these two technologies to this one. But when we say we have to supply steam, that means we have to supply energy somewhere else to produce steam from water. Right? And good thing about this one is, this can be integrated with other industries. What we saw in the morning, that we have steam co-production, and nobody is there to give us value for this steam. We cannot sell this steam. Sometimes, in some cases, I've also seen even the steam is sent to the air cooler and just condensed and energy is lost. So, from integration point of view, there's a lot of advantages. So you have high efficiency, and somewhere you get very cheap steam, which can be used to produce hydrogen at very high efficiencies. So as I said, currently still under development. Right? And since it's still under development, cost is pretty high. So once economy of scale comes in, we start producing a lot of electrolyzer stacks, and then the price will definitely come down. So CO2 footprint for hydrogen, I think we talked about this slightly last time. But we saw in the morning that for producing 1 kg of hydrogen, we need somewhere around 14 megajoule of energy. Right? And we also did the costing, that's somewhere around 1.5. We saw from one of the graph in the morning, we produced globally somewhere around 90-95 million ton of hydrogen globally. And 1 kg of hydrogen releases somewhere around 10 kg of CO2. If you do a simple calculation with the reactions we saw in the morning, CH4 plus twice H2O gives CO2 plus H2. You can already see you end up already somewhere around 5 or 6. And then as I said, 40%, 30% is coming from fuel burning. So if 1 kg of hydrogen releases somewhere around 10 kg of CO2. 95 times 10, you already see almost 1 billion tons of CO2 annually is only because of hydrogen production. And we saw yesterday the annual CO2 emission globally is somewhere around 30. So hydrogen industry is a major CO2 emitter, no? So almost 3%. So on the first slide we saw different colors of hydrogen, and as we said the main colors are basically grey, blue and green. Anything else is somewhere in between. So here I am showing just a small comparison how the CO2 footprint and cost wise they look or compare with each other. Right? So let's stay with first two first of all. So the grey, this number we saw in the morning already, 1.5 euros per kg of hydrogen, that's my production cost. CO2 footprint we saw somewhere around 10. And the blue one 2.5. And as you said, we can only capture 95%. For sake of simplicity, I assume now that I capture 90% of this CO2, then I am left with only 1. But actually, capturing will also cost some energy, right? And this will also release some CO2. So capturing 90% CO2, that means you avoided 85%. So that's the difference between capturing and avoiding. Right? Because when you capture 90%, you need some energy. For this energy, you're also releasing carbon dioxide. So effectively, we are avoiding only 85%. Capturing is 90%, but avoiding 85%. Because for this energy, we are releasing CO2 somewhere else as well. Right? So that's how this 10 became 1.5 for the blue. Right? Now, yesterday we talked about this, why somebody will start capturing CO2 or why somebody will start producing blue hydrogen suddenly. So we talked about this carbon price, carbon taxes. So let's assume there is a carbon tax of certain euros per ton, right? But what it means, if you are emitting some CO2, for every ton of CO2 you have to pay, let's say 100, 120 euro, right? So I just try to calculate at what carbon tax people will start moving from grey to blue, and it's around 118 euros per ton. So 1.5, I simply do a mathematics here. So I try to do these two, match these two numbers by varying my carbon tax. So what it means that somewhere around carbon tax of 120, the blue hydrogen starts making sense. Carbon tax is not existing currently in many countries. Only few countries started with this carbon tax system. Netherlands is one, and they set 120. So in Netherlands, you can say based on these assumptions, blue hydrogen, everybody is moving from grey hydrogen to blue hydrogen because they can do 1.5. They can produce at 1.5, keep emitting 10 kg per ton, but then they have to pay 120 euro to government as tax, right? We saw yesterday electricity production from coal to renewable power, what's the cost difference, and this famous line, getting clean is expensive, right? This is what we see here as well, the hydrogen price of 1.5 from grey and 6.5 to green. So for electricity, the ratio was 2, but for hydrogen, the ratio is almost 5, right? So 1.5, almost 6.5 here. So why people will start using, producing is fine, but why somebody will start using green hydrogen and pay 5 times more price? So once again, the similar comparison or similar sensitivity. So if the CO2 tax become even higher, 505, then the price of grey hydrogen is matching with the green. So this kind of CO2 tax we need to really push people to start using green hydrogen instead of grey hydrogen, right? Just to extend it further, did the same calculation or same comparison between blue and green. So we started with green and blue, grey and blue, and the grey and green. And now you could see very high CO2 tax required to match blue with the green. Right? questions? You capture carbon dioxide, put it in your beverages, drink your cola, and CO2 is released. That's the pressure on the CCU route, right? Once again, to repeat, energy transition we talked yesterday for electricity, industrial heating. We saw this slide yesterday as well, the disparity between the locations. As we said, we are blessed, we are somewhere around here, 2,400 hours of good sunshine every year. Some countries like European and Russian, Northern Russian, they are not so blessed. Right? So CO2 footprint of grey hydrogen, you could see China suddenly sharp increase in the total mix, and that is in parallel to their growth story from 2000 to 2020. They started consuming a lot of hydrogen, and as we said in the morning, as in India, compared to India where we have most of hydrogen production by natural gas, in China it's mostly by coal gasification, which is even more CO2 intensive. So we saw yesterday already for the electricity. Now we will see the same thing for hydrogen. Unfortunately, renewable potential at place where consumption is low. So you could see the northern African regions, Middle Eastern regions, they have very good solar radiation, also solar potential. But if you look at the consumption, it's only this much, right? So what we can do, we produce at low cost places. You produce, let's say, hydrogen via electrolysis here and transfer it to the locations where it is required. So most consumers are in this region, Northern Europe and Northern America, right? But we saw yesterday already talked about this transport of energy from one place to another place. We talked in terms of electricity. Losses somewhere around 8% for 1500 kilometer, transmission and distribution losses. If you can correlate with the high school electrical courses, power is voltage times current, right? And your losses are I times I square, current times resistance square. And that's the reason why for the long transmission lines they always ramp up the voltage. Up to 140 kilovolt or even higher. While at home we use 220 volt. So if they start transmitting electricity at 220 volt, you will get hardly anything at home. Everything will be lost. So that's okay for short distances. We see 8% for 1500 kilometer. So within country like India, that's fine. In Europe, within countries, one country is also acceptable. 1500, 2000, you already crossed 3-4 countries there. So there also it's fine. But if you are talking about intercontinental, because we want to produce here cheaply and transfer it there, which is something like 7,000, 8,000 kilometer. Similarly, 4,000, 5,000 kilometer here. That's not a good idea. Another issue is there's a big ocean here, and overhead transmission lines are relatively cheaper. You can do that, but subsea lines are very expensive. So first of all, if you are talking about 5,000 kilometer, you already have 30% losses. You have to invest huge amount of money. So the difference what we had in electricity, 174, 79, if you remember from yesterday, everything is lost, right? What we can do, we can transfer this electrical energy into chemical energy somehow, right? And transfer this chemical energy stored in the compound and transfer this compound, right? So what is the main requirement for this compound? It should have high energy density.
So you're transferring 1 kg of compound or whatever material. It must have very high energy density, very high energy content. It should be ideally non-toxic, non-flammable, non-explosive. Right? Should be socially accepted. Yesterday somebody was making a comment, hydrogen for mobility, yes, but you also don't want to see hydrogen, people are scared, those kind of things also. Socially should be accepted for the society. Unfortunately, we do not have any such compound which fits all these requirements. That people accept it, and it's non-toxic, non-flammable, non-explosive. There is only one thing we talked this morning is steam, water, which can carry a lot of energy, but transferring steam from one place to another, you could imagine lot of heat losses, lot of condensation, so it's also not a good idea for kilometers and kilometers. For few hundred meters that's fine within the plant, but not in. Yeah. So in next coming few slides we'll see comparison between 4 methods. What we can do, lot of electricity, solar electricity here, green electricity here. You produce hydrogen here. You can liquefy hydrogen here, and via tankers, ship tankers, you can transport it somewhere else. Right? That's one method. So that's the first one is you don't change your component, you don't change your compound. But what else we can do? We convert this green hydrogen produced somewhere in Middle East or Northern Africa into synthetic natural gas from the renewable hydrogen, and transport this natural gas to somewhere else, convert it once again to hydrogen with the process, using the process what we saw in the morning, the steam methane reforming, and use hydrogen there. Or the synthetic natural gas can also be used directly. Right? We'll see in coming slides in detail about these processes. There are some other organic compounds. So this is like direct conversion, and this one is second one gives us opportunity to use the energy directly as natural gas at the location where it is required, or we use it, we convert it to hydrogen and then use it, right? There is another way. There are some organic compounds which you can hydrogenate. So hydrogenation means addition of hydrogen at one location. You transport these compounds somewhere else and then dehydrogenate it and release hydrogen you can use further. Right? So that's another way. Another interesting compound is ammonia. Haber-Bosch we talked yesterday about. So you generate green hydrogen, convert it to ammonia, and transport ammonia, and then once again crack the ammonia between hydrogen and nitrogen. Nitrogen you release into atmosphere, hydrogen you use. So the first one, as we said, you simply generate in the Middle Eastern or Northern African regions where the renewable power price is low. If you remember from yesterday, 174.89 or 79, sorry. So you generate hydrogen by electrolysis where the price is somewhere around 80, right? You liquefy it, and via tankers you ship it to somewhere, you regasify it and go to the hydrogen network, right, to use. Now, problem with this method is electrolyzer efficiency is coming up, new methods coming up, we are reaching 80%, fine for this step. Problem is with this step. We saw in the morning the boiling point is very low for hydrogen, minus 252 degrees centigrade. That means a lot of energy is required to create this cold temperature. Right? And within this step, you lose almost 25% of your energy. So every step you need electrical power. So whatever hydrogen you put in, some electricity you have to put in. What comes out is only 70% of what you put in as hydrogen. So 30% already lost here. Now, hydrogen being the lightest component, another problem. And when you transport these into the ship, it's liquefied at minus 252 degrees centigrade. It means it's very cold. And these voyages can take up to 3 days, 4 days. And you could imagine a lot of heat radiation into these tanks, although they are well insulated, but still you have a lot of heat ingress. That means you will always have some gas, some liquid boiling. Right? That's actually called boil off during the journey from point A to point B. Sometimes this boil off gas is recovered because you have to supply electrical power. You can compress it back, so it's not lost. But sometimes electrical power on ship, you could imagine, very expensive. So sometimes this boil off gas is simply vented off. So because of its inherent characteristics, very low temperature, right, and very low molecular weight, there's a lot of boil off during the journey. Right? So that's also another disadvantage of this process. You regasify. Regasify means you reach at liquid condition and you simply boil it. Right? Since the temperature is minus 252, it's a very good thing. You could use this cold energy, refrigeration, some other process where you need really cold temperature. So you could do some integration here with some other industries where you need cold temperatures, but if it's not there, then regasification will also cost something. There's efficiency loss, another 2-3%. It's not much, but there's some efficiency loss here in this step as well. So altogether, it's not a very good idea. People are doing it because no other option is available at the moment, but the round trip efficiency going from this point to this point is somewhere around 50%. You lose already 70% here. That's no number. So the next one, synthetic natural gas. You take CO2, generate renewable hydrogen and convert it to methane, water is simply discarded. The advantage of this route is natural gas society is handling for last 100 years, a little bit less than 100 years, but it's a very established technology, very established supply chain. And there are some hard to abate industries which we talked about yesterday. There we cannot replace natural gas, so we continue. So natural gas will be there in some of the applications, right? And if this natural gas is not the natural gas exploited from gas fields, it can be considered as clean. We'll come to this in a few minutes. But all in all, natural gas will be there. We use in hard to abate industry, and also as an established one, infrastructure is there, pipelines are there, so everything is there. It's just the method we could generate or produce natural gas is different, but that's a strong advantage of this route. The major disadvantage with this one is if you are using this natural gas somewhere else, CO2 is released. So solution for this is what you do, you generate, as we saw on the previous slide, you generate green hydrogen by electrolysis, right? You do methylation, that's this reaction, right? You combine CO2, where this CO2 is coming from. So generally, you have this CO2 either by burning natural gas or something else, right? But in this case, we'll come to this later. So you generate natural gas and liquefy it, which is also very well established technology, LNG. Probably everybody has heard about liquefied natural gas. You ship it, there are almost 700, 800 LNG ships operating every day. It's a very well established supply chain, everybody is familiar with this. And you receive liquefied natural gas, gasify it, and produce hydrogen gas using process Samarpit, which we saw in the morning in detail, right? So this is conventional, well established. This is well established. This is very well established. So that's a major advantage of this route. You are doing something new. It is also pretty much established, right? The only new thing you are doing here is you are capturing CO2 in this process, and the captured CO2 goes back. So what people are proposing is a ship will bring natural gas, right? It will unload all the liquefied natural gas to the plant, stay there, and this plant will produce CO2, and this CO2 will be put in the same ship. The same ship will be go, otherwise the ship will be going empty. Right? So you make use of the same ship, it goes to the other location, taking the CO2, giving this CO2 to this methanation process, and that's how CO2 is only traveling here to here. So there is no additional CO2 emission apart from some boil off. But boil off in CO2 transport is much lower because does somebody know boiling point of CO2? Minus 57 compared to minus 252, it's much lower. So you have much lower heat ingress, much lower boil off. So that's basically this showed some advantages, some disadvantages. It's very new. People have already started building plants and transporting CO2, but actually they are transporting on one side energy. So this is energy carriers, right? Energy transport, and other side you are just transporting this CO2 because this CO2 is mixed with your hydrogen and then it becomes a molecule which is carrying actually the energy. We'll see in coming slides there is another major disadvantage with this one, or maybe we can discuss already here. So hydrogen being the lightest gas, even after liquefying, the density is somewhere around 80 kg per meter cube. Right? Compare this with the water, it's 1000 kg per meter cube. So much lighter liquid. Even when liquefied is much lighter. So when we were transporting liquid hydrogen, we had pure hydrogen, lot of energy in 1 kg, right? But now you could see if we compare hydrogen with natural gas, right? So if we have 1 kg of liquid hydrogen, we need how much? 16 by 4 kg of natural gas. Right? So actually in the same ship, so the ship transport you could imagine is based on per kg. What do you have as a measure? It's the weight which is defining your fuel consumption for the ship transport, right? So when I'm transporting liquid hydrogen, for example 1 kg, if I do it via methane, it's only 4 by 16, right? That means my transportation cost for this route will be much higher because I'm transporting much lower hydrogen compared to pure hydrogen. Right? Okay, the third one is organic components. So toluene and methyl cyclohexane are some examples. So you do hydrogenation and dehydrogenation, as I said. Advantage of this method is the operating conditions are mild, or let's say milder than others, so 20 bar to 20 degrees centigrade. And round trip efficiency is lower compared to H2 and SMG as carrier, right? But the disadvantage is you still have some hydrocarbons in your chain. And when we are talking about the zero carbon economy, there will be no crude oil, there will be no hydrocarbons, so there will be no toluene or methyl cyclohexanes coming out, right? So that's the major disadvantage we are talking about for this one. But as we said, you generate once again renewable hydrogen, you hydrogenate it, right? You transport it, you dehydrogenate and take the hydrogen to your network or to your use. You generate the same compound what you started here. In the same ship, you put the same compound, goes back, it's rotating like this. So that's another way of carrying the energy from one location to another location. And just to repeat once again, this energy, solar PV disparity in radiation, that brings this option, this idea to generate solar energy or hydrogen, green hydrogen in one location where the renewable power cost is low and transport it to the place where we need it. Then the last one is ammonia. So ammonia very well known, used in refrigeration and many other applications. Transporting ammonia is also very well established. Liquid ammonia density is somewhere around 760 kg per meter cube, not like very low like liquid hydrogen. So you could transport a lot of ammonia in your tankers, right? Yeah, I already said ammonia already 100-year-old technology similar to SMR what we discussed in detail this morning. The major advantage of this route is the round efficiency is much higher compared to others. It's almost 90%. What it means, if you go from here to here, you have only losses of 10%, 15%. Right? So that's a major advantage. One disadvantage is ammonia is highly toxic, not highly toxic but toxic, right? Corrosive, and handling needs a lot of additional safety infrastructure. Capex becomes high, so small ammonia use is fine, but if you have higher capacity and within your plant ammonia inventory is above certain limit, you need to install a lot of safety measures. It increases your capital costs. So you are ending up here with ammonia, and then you can crack this ammonia to get your hydrogen. The nitrogen is released. Good thing about this is you do not have any transport back, which this ship of course will go empty back, but will not use as much as fuel as something else. So at the end of the day, the overall cost is much lower for this route, right? You can also people are also starting to think about using ammonia directly, because this route will also have some efficiency loss. So what you can do, you can directly use your ammonia. Some gas turbines are already using ammonia with natural gas. So slowly they are increasing ammonia content in their fuel to generate power. But ammonia conversion is not easy. It's a very lazy combustion. The flame is not stable, so it's a lot of problems. Another major disadvantage using ammonia as direct fuel is, we talked about it yesterday, high NOx emissions, because you have ammonia and oxygen and at high flame temperature, NOx concentration, NOx emissions are much higher. So you need more investment to clean your flue gas. So some qualitative comparison between these four methods. A lot of numbers here, but we'll spend 5-10 minutes on this slide. One way is, as I said yesterday, we saw the difference between the renewable power 174 and 84, right? And we are talking about, or we talked about in last 15-20 minutes, that we can generate at low cost and transport it to somewhere else via 4 different methods, right? So the first column you see here is, let's say, at high cost center or cost place, you generate renewable power at a cost of almost 9 euro per kg of hydrogen. Then you don't have any shipping cost, you don't have any boil off. It's the same. So you are at the same location, so this price is similar. You will understand more when we go to the next column. Then we talked about 4 different methods, right, that we liquefied. Now we are generating somewhere in Middle East, Northern Africa at very low price of renewable power. Right? And so you could already see the hydrogen production price by electrolysis is much lower compared to this location. So I generated 4.3 H2 carrier. So from this step to this step is the liquefaction process. So I liquefy, I generate at 4.31, but then I have to put a lot of energy to liquefy it. It's already at 8.21. Then shipping costs somewhere around €0.25 per kg of hydrogen. Boil off somewhere around 0.1. So I landed at another location at 8.55. then we have to gasify it. It's somewhere around 9.4. So you could already see if you are at this location with a renewable power price is 174, it's still better to produce hydrogen there instead of producing somewhere else and take all this pain. But end of the day, I have to pay high price for my hydrogen. Right? So that's the first one, just a quantitative comparison. The synthetic natural gas route, you could see the efficiency loss from gasification, or let's say where you generate hydrogen and go to the carrier state, it's not so much. So what we do, we generate at the same price because generation is same, which depends on this price. This is 4.31 still, but the hydrogen which goes into my carrier as synthetic natural gas, its price is slightly lower because the efficiency is a little bit more. We talked on this a few minutes ago that since you have synthetic natural gas, you are transferring less hydrogen actually. It's more carbon, what's inside your ship. So you could see your shipping cost will be higher. Right? So you save something here, this difference, but then you pay more here. Right? Point of is goes lower. So landed price is similar, but then you have to crack this back or convert this to hydrogen, which is 10.75. So it's still higher. Then we talked about these organic components, which we can hydrogenate and dehydrogenate. Another location, you could already see same price, conversion, hydrogenation is at milder conditions, efficiency is more. So the hydrogen which goes in form of these organic compounds into your carrier is much lower compared to other things. Right? But then once again, higher the molecular weight of component which you are transporting, less is the hydrogen you are transporting. Right? So in terms of per kg of shipping cost for hydrogen, it's even higher because these organic compounds are toluene, ethyl, cyclohexane, and the molecular weight is much higher. Right? So, or let's say C2H ratio is very high, so it's simply transporting carbon and other components, transporting it back. Yeah, once again the hydrogen shipping cost is much higher for this route. The vapor pressure is much lower, so there is no boil off as such. It's no losses in the boil off. Lands at 8.5, but you still have to dehydrogenate it. That also costs something, so you have to have 9.76. But then look at ammonia. You generate once again at 4.31 like other four methods. From ammonia to from hydrogen to ammonia, efficiency loss is not so high. It's a very well established one technology. 5.4 very low. What goes to the carrier? There are some boil off losses somewhere between organic components and synthetic natural gas. Sorry, shipping costs, but no boil off. It landed at 6.85, and cracking ammonia is also very similar to SMR cost what we saw in the morning. So also we can say very well established technology. And there we have the lower price than generating hydrogen. So what we see from these tables, and we should not draw any conclusion, this is just for comparison purposes. But at the moment, generating hydrogen at location where renewable power is high, there are some methods where you can transport energy. There are components or compounds which can act as energy carrier. That's why this term comes up, energy carrier. But that's how the economics looks like at the moment. And ammonia, since ammonia shows huge potential, that's why there are a lot of ammonia transportation and ammonia synthesis using ammonia renewable hydrogen projects are coming up. Similarly, on the other side of the world, you have to crack this ammonia, so ammonia cracking plants are also coming up. But But as we said, disadvantage of this route is ammonia safety issues, right? And when we talk about tankers, we're talking about 60,000 tons of ammonia transportation, right? So on sea, it's not very sure, it's only a few people on the ship. But when this ammonia is transported to shore, then you have huge ammonia tank farms, and there it's serious issue. So that's a major disadvantage. But yes, at the moment, research work is continuing on these steps, but this is already kind of industrialized, so a lot of ammonia transportation, ammonia capture plants coming. Yeah, so we saw at the moment only 4 carriers, but there are others out there. But, to keep it simple, I included only 4 for now, which have already passed the conceptual stage, right? But people are still looking for new carriers, and the main criteria we saw already should be low in toxicity, low in flammability. It should have high energy density, low molecular weight. Should be in a transportable condition where you do not have boil-off losses. So to keep the shipping cost, boil-off cost low. People are also focusing on increasing efficiency of different steps, where you do hydrogenation, dehydrogenation. So a lot of efforts at the moment on organic carrier, hydrogenation, dehydrogenation steps, efficiency increase. So for example, we talked about the integration, right? So you transport liquid hydrogen, it comes at shore, and you have to gasify it, and there is nobody who can make use of this cold liquid at very low temperature. You just have to gasify it using air or cooling water, river water, sea water, whatever. It means energy is lost in atmosphere, right? So integration scheme people are heavily looking at to have synergies between 2 processes, 3 processes. So kind of hub model. They start to build all these regasification plants at one location or a location where other industries are there or consumers for refrigerations are there. Right? So kind of what we call here is economic zone, where you have a lot of industries coming in, and then they find synergies between them to have overall optimization. You could already see you're generating renewable hydrogen somewhere in North Africa, Middle East, transporting it. It's a collaborative effort, not between 2 companies, 2 societies, but 2 countries or different countries rather, because these operators, ship operators come from a different country, you are generating somewhere else, you are transporting it to somewhere else. Yeah, it's a major collaborative effort. We already saw there is no one solution which fits all. So at some locations where you can find some integration schemes, probably liquid hydrogen transportation is cheaper. So there is no one solution for which can be applied to all locations, all countries, all. Each, as we already saw, each has advantages, disadvantages, and solution is very specific to country location. Yeah. We already talked about such ideas need supportive government policies. Yeah, I think that's it from my side. Questions? So steam is not something new to human society. Almost 200 years ago was already the potential of steam was already discovered by Greeks, and then humans kept on improving the steam, let's say generation and utilization with the steam engines, several steam engines. You could see 500, 600 years ago such steam systems were used, and then 100 years ago, I don't know if you Most of you will see running these steam engines for the trains or between the trains. And today we have, so in the starting it was only atmospheric pressure, very small amount of steam was used. So basically you fire wood, generate steam, connected in pipe, and then steam is coming out from these nozzles, and these things starts moving, and you make use of this rotational power, right? 1 bar 50, very small amount. Now we are talking about almost 300 bar of steam generation, 1500 tons per hour, gigawatt of power plants. So we have came a long way. So as I said, we will go back to the basics. That's a typical temperature pressure curve. As we said in the morning also, higher the temperature, higher is the pressure, or the other way around, higher is the steam generation pressure, higher will be the saturation temperature. That's the liquid side, that's the steam side. The temperature enthalpy curve for water looks like this. Somebody mentioned something like a supercritical state. So you kept increasing pressure. At certain point, the property of water and vapor are more or less similar. So that's this point, supercriticality. That's the superheated, saturated vapor line, superheated, saturated liquid line. On the left side is the subcooled region. On the right side is the superheated. So if you have conditions in this area, we are in superheated state, right? It's actually not so visible, but I'll guide you through. So that's how a steam table looks like. And what steam table provides you is all the properties of steam. Sorry, this is not readable, but 2 or 3 things we'll talk about. So there are 3 for energy balance and or heat balance. There are 2 or 3 main things. What's the enthalpy of liquid state? What's the enthalpy of vaporization? And what's the enthalpy of superheating? So you could see here, I read it for you. It's not readable, but here you could see that's the enthalpy of liquid state. It's around 420 at 100 degrees centigrade. This you can calculate back from your formula, MCPDT. If you remember, CP of water 4.187, go from 100 to 0, 0 is your reference state, is 490, which you can see here. Right? Similarly, you have enthalpy of vaporization also, which is somewhere around 2243 at this temperature. And you could see enthalpy of liquid plus this will give you enthalpy of vapor. Right? Now this steam table is currently only for saturated condition. So enthalpy of vapor, what is mentioned here, is for the saturated vapor, saturated steam. But if you increase the temperature of steam, heat the steam further, it becomes superheated. And you apply on the liquid side this formula, you will apply similar formula on the steam side or the vapor side. The only difference would be Cp would be for the steam. So like Cp for water is around 4.2, it's somewhere around 1.92 for steam, if I remember correctly. Right? So similar way, if you have superheated steam, enthalpy of your saturated steam plus MCPDT, whatever temperature you are superheating above saturation temperature, that will give you enthalpy of superheated steam, right? Do you remember what's the name of this diagram? Anybody remember? Remember Boiler diagram? So that's the, once again, pressure enthalpy. We saw earlier temperature enthalpy. This is pressure enthalpy Boiler diagram for water system. This curve is familiar from the previous slide, right? Now we have different curves. This represents entropy. And there are other curves here. This represents your vapor fraction. So we saw in previous sessions and in earlier slides as well. So you can use thermal energy of steam by condensing it. You can subcool water. You can have superheated steam. So in coming 5-10 slides, we'll see how all these processes are represented here on this slide. Right? So the first one would be, so let's say we have 10 bar steam, right? 10 bar corresponds to 180 degrees centigrade. This comes from comes from this curve. So somewhere around 10 bar, we are at 180 degrees, right? Okay, so as I was saying, we have 10 bar steam. From the steam table, we know our enthalpy is 2780 kilojoule per kg. Vapor fraction is 1. We said it's saturated steam, right? And this point A is represented somewhere here because we said earlier that's the point, that's the curve for saturated steam, right? So if you have vapor fraction 1, it's saturated, and 10 bar and 180 degree represents somewhere here. So you could see 10 bar with 2780. Yeah? So we are somewhere here, right? And if we talk about condensing the steam, condensing means we are at the same pressure, right? At the same pressure, we are just changing the vapor fraction from 1 to 0. As we said, this is the saturated liquid line, this is the saturated vapor line. We were here, we started here, and we cool it from here to here, thereby reducing the vapor fraction from 1 to 0. At this point, you can already read or calculate even based on MCPDT, already see what's the enthalpy of our steam at point B, somewhere around 763. Means if I go from point A to B, which is saturated steam to saturated liquid, we can extract how much? Almost 2000 kilojoule per kg. Let's stay here. Yeah, this 2000 kilojoule per kg energy can be used, thermal energy, right? And pressure of steam depends on temperature at which heat is required. So let's say heat is required for your process heating at 150 degree, and you know heat transfer from high to low temperature, and there is a certain delta T. We will talk about this 20 degree, 30 degree for different application, and that's how you specify or decide on your temperature of steam. And temperature of steam is nothing but pressure of steam, based on the curve, the temperature pressure curve what we saw, right? So normally at cooking tea or boiling milk or water at home, normally we do it at 1 bar, because 100 degree centigrade is enough, right? Then to increase efficiency, you apply pressure cooking. What exactly we do with pressure cooking? We increase the pressure, and that means the temperature of water inside the pressure cooker is increased. Yeah? So that's how you increase the efficiency, right? Process heating is somewhere around 80 to 250. We said this morning 300, somewhere around this range, 250, 300 degrees centigrade. You need process heating. Right? We also talked about the steam flow from one point to another point. It creates a lot of pressure drop. So this also we need to keep in mind. So we are going from A to here, but B is still here. That's my mistake. So once again, we start with the same 10 bar, 180 degree saturated steam, and instead of condensing it, now we are going to expand it. So earlier we saw extracting heat from steam at same pressure. Now we are expanding it from 10 bar to 1 bar. It's on the logarithmic log scale. Right? So another small mistake here, should be 1 actually. So we go from 10 bar to 1 bar. you could see enthalpy at the starting point was similar 2780, go from here to here, enthalpy is somewhere 2250. Means with this state change, how much energy we are extracting? Only 524 per kg of steam. And you could see that going from reducing the pressure, you can only extract very small amount of energy, right? While going on this line parallel to the x-axis, you can extract a lot of energy. So to extract similar amount of energy, you really have to go, if you want to extract this minus this, you really have to go very high pressure to very low pressure, which is practically not possible. Right? So if you want to extract kinetic energy from steam, what would you prefer? What would you prefer? You move a little bit up it on this curve. That means generate steam at higher pressure. Thereby you increase the enthalpy of 0.8, where you could see 2803. So earlier we saw the enthalpy was 2780 at 10 bar, but now I am generating steam at 30 bar, right? So starting point enthalpy is increased, right? Point B is similar, 1 bar. Now I am extracting a little bit more energy, right? 10% more, 524 to 587. Still not comparable to what we had with the condensation, right? Because yesterday somebody said the major part of energy content of steam is in latent heat. Right? What else we can do? What else we can do? We can superheat the steam, right? So we are not at the saturation curve, but now we move from saturation curve to superheated region, thereby increasing the enthalpy of point A. Right? And with this, now you have much more energy extraction. Right? So we are already coming to this point that if we want to have kinetic energy extraction from steam, it's better to have wide difference between pressure between point A and B, right? And if you want to have process heating or thermal energy extraction from steam, higher the temperature required for process, higher will be the pressure required for your steam generation. Right? Okay, this you pretty much understood or explained. And as I was saying earlier 19th century, they were generating power using very low pressure steam. Nowadays, supercritical, somebody has also heard about ultra supercritical power generation. It's at 300 bar somewhere here, so it's already here. So supercritical was 240 somewhere in this region, but now they are talking about 300 bar somewhere in this region already. So what we saw till now is the steam and conceptually basically how its properties are and how we can utilize the state change of steam for our industrial purposes. Right? So heating and electricity production, that's what we already talked about, the two major applications we found. Right? So let's take an example. We need to heat a certain process steam from 10 kg per second from 30 degree to 150 degree centigrade. Cp is 2.5. Can you please calculate what's the duty required? What will be the duty required in kilowatt? That's my mass flow rate. I have the Cp, I have temperature in, temperature out. What will be the duty? How much? 3,000? I don't know, let's check. Anyone else other than 3,000? 3,000? So I was not wrong. So this delta T we already talked about. We already know that the heat flows from high temperature to low temperature. But you cannot have heat transfer from 29.01 degree to 29 degree. You need certain temperature difference. And significance of this temperature difference is higher this delta T, because delta T is the driving force for heat transfer, like for mass transfer driving forces. Sorry? Concentration difference, right? So similarly for heat transfer driving forces, temperature difference, and rate is like driving force divided by resistance, if I remember correctly. Right? So if you have lower temperature difference, your driving force is low, that means your heat transfer rate is low, you need a lot of heat transfer area. Right? So delta T we already talked about. That means, let's assume for this application we need 20 degrees centigrade delta T. So we are heating the steam from 30 degree to 150 degree, right? And we said minimum temperature difference we need is 20 degree. That means on this end we need to have steam at 170 degrees. That fix is our pressure from the same curve what we saw in the starting temperature pressure saturation curve, which is somewhere around 8 bar. So at 8 bar we go to the steam table what we saw earlier. That our latent heat of condensation is this much, 2032, sorry, right? Which is 5.3 tons per hour. Right? So what we have so far, we started here. We know we need 3,000 kilowatt of duty to be supplied, right? Then we already calculated that 5.3 tons per hour of steam is required. We go from point A to point B, what we saw in the first temperature enthalpy curve, right? And thereby extracting 3,000 kilowatt of energy, right? Where this steam will be generated, so already by burning fuel. So the same numbers we use, what we use so far. Let's assume that we are burning natural gas, 47 megajoule per kg, lower heating value, already gives you what's the amount of natural gas we need. Okay, this steam is generated, you need water, so this water is kind of recirculating. You take the steam, it goes back here, comes back here, it keeps circulating within the system. When you burn natural gas, you generate a lot of flue gases. So to burn this natural gas or methane, you need air. So if you do a simple stoichiometric calculation, that will give you amount of air based on very simple 79-21 mole composition, nitrogen and oxygen, right? That gives me already amount of flue gas, right? Let's assume if we have two such consumers, 3000 kilowatt here, 3000 kilowatt here, suddenly our natural gas consumption increased from 313 to 626. Right? We are generating steam not 5.3 but now 10.6. So you have, let's say, two consumers for your thermal energy. Yeah? Let's skip this one. Yeah, this one. So in the previous slide, we saw we have two consumers which requires heat at similar temperature. But now assume we have two different consumers. One requires heat at 150, another one requires heat at 200 degrees centigrade. Right? So based on this 150, we calculated earlier that the steam temperature required is 170, but now suddenly we need steam at 220, right? So what you will do, you will burn natural gas here, generate steam at 170 or 8 bar. For this application, you generate steam at higher pressure, probably 23 bar, right? This also is coming from this similar same TP curve for the steam what we saw in this time. But actually, it's not a good idea that you have two steam generation systems separately, right? What you can do, first you generate steam at high pressure, supply steam at high temperature or high pressure to this consumer, and the remaining steam you can simply let down, right? With this, what we did, we save all these systems here, right? So one is high pressure system, one is low pressure system. Instead of this, you will utilize only one high pressure system, generate steam at high pressure, and supply it at two different pressure levels. Same thing if we see or try to locate on the modular diagram, will look like this. A to B, you go from flashing the saturated steam, right? So if we flash the steam, or let's say if we reduce the pressure of steam, what will happen? You will have some condensation. And why is that? Generally, it's not normal for other gases or other components, but for steam. Why is that? Does somebody know? So latent heat of steam it's unfortunate that we cannot read it, but latent heat of steam, how does it change with the temperature? So at higher temperature, latent heat of steam is lower. That means if I need certain duty and at higher temperature, the amount of steam required is more because latent heat is low. Right? Imagine we have saturated steam at higher temperature, latent heat at this temperature is low, and suddenly you reduce the pressure. So at condition B, your latent heat is more, right? And if you assume it's a derivative process, somewhere this energy must come from. And this energy will come from condensation. That's why whenever you reduce pressure of a saturated steam, you will always have some condensation, right? Exactly where. So as I said, as pressure increases, latent heat of evaporation of water decreases, right? And this increase or delta in latent heat must be supplied by some part of steam condensed, right? Now here you could see based on condensation temperature or pressure, we have almost 20-25% of energy is still left in the steam. Actually, it's not steam; it's after condensation it becomes water, right? So I think we saw 2,700 to 490. So almost 25% energy is still left, condensed water. And as I said, condensed water will be recycled back, so it's a closed system. So if we see that in the TQ diagram, so this is a typical temperature enthalpy diagram. What we see here, before that, so we did this, right? And we have a lot of, we saw in the morning also there was a lot of waste heat available in the flue gas. You want to recover it, right? So we already recovered a lot of energy here, right? But you can make use of some energy from this flue gas as well. And that's what we see here. We're cooling the flue gas from T1 to T2. This is typically, we saw in the morning also 150, 160, and then gas goes out of the stack to atmosphere, right? And steam generation at 6 bar, which corresponds to, I don't know, 160, 170 degrees centigrade, right? So steam generation means you supply a lot of enthalpy at the same temperature. That's why the curve is like this, right? You cool the flue gas from certain temperature up to this temperature. That's the minimum approach temperature we talked about. In our example earlier, we saw 20 degrees. Right? We'll see in the coming slides what are the optimum temperature difference for different applications, different services. But for a typical flue gas and steam generation, it's somewhere around 14-50 degrees. So that's 40-50 degrees. Now this is the recovered heat from flue gas, but this is what is kind of lost, right? Now we do steam generation. What you want to do is you want to generate steam at high pressure, right? So if I am generating steam from flue gas, what we'll see here, if I, instead of 6 bar, if I generate steam only at 10 bar, right? And I know that's the temperature difference, and beyond this point on the left side will be the energy lost, right, in the flue gas. So higher the steam generation pressure, more is the energy lost to atmosphere, right? But sometimes this pressure is defined by your requirement, process requirement. Probably like we saw a process steam to be heated from 30 degree to 150 degree. This defined 170 degree, which in turn means 8 bar, the pressure of steam generation. So higher the steam generation pressure, more will be the loss. But what you can do, you can generate steam at 2 different pressure levels. We saw that in one of the examples, where for one application you need 220 degree, for another one you need only 150 degree. So you generate it at 23 bar and 8 bar. Right? Let's typically plot plan how a industrial site looks like. And we're talking about here maybe 200 meter by 200 meter. That means you generate steam, but you also have to move it around. Maybe your one exchanger or one consumer is here and another one is here. So you will have steam headers transferring your generated steam. What it means? It means surface heat losses. So 220 degree steam header, you will have a lot of heat losses. And we saw if these headers are saturated steam header, any heat loss will result in before temperature drop, condensation, right? Because it's at saturation temperature, so any heat coming out from this system will result into condensation. So if you have, what can happen if you have condensation in your steam pipes, you will have water droplet. And we already know the density difference between steam and water is huge. The water is somewhere around 1000 at 1 bar, and similarly steam is somewhere around 30. So if you have sudden decrease in density, this can create water hammer. So droplets can travel very fast and hit the bends of the pipe where the pipe is bending somewhere else, and they are so fast that they can break the pipe. So it's a major issue. So what normally is done, every 20-30 meter or sometimes 100 meter, you have steam traps, right? It's a kind of equipment where you trap any condensation of water. Right? Any water is condensed. The pipes are on grade, so they are slightly slow. Any water condensed goes into these steam traps, and they work in this way that only the condensed water comes out and no steam is coming out if these are operated properly. Right? So if you look at the energy balance, energy in, out, what we are putting in is the LHV of fuel, right? What is coming out is steam used in heat exchanger or boiler, right? What are the energy losses we saw so far? Surface heat losses. We talked about these pipes, long pipes within your plant. And how we can reduce the surface heat losses? Insulation. And the insulation thickness, you increase the insulation thickness. Sorry?
Critical thickness of insulation.
There is a critical thickness of insulation. So it's not always you increase the insulation thickness and your heat loss will go down. sometimes it even increases because you are increasing the area. And you are hindering the heat loss, but you are increasing the area, so the heat loss is actually Q by A. And if area increases, your
Q is also increases.
Q also increases. So we have mainly the surface heat loss and the chimney losses. Chimney loss is the energy which we cannot extract from flue gas. We have to send it to atmosphere via chimney. The leakage, we talked about these steam traps. So as I said, if they are operating properly, but most of the time, unfortunately, they do not operate. They do not trap condensed water, but sometimes they also remove valuable steam. So that's also kind of loss. Water as such is not corrosive, right? But water mixed with carbon dioxide or any other dissolved gases, or not all, but some dissolved gases is highly corrosive. So in such systems, you need to put some chemicals in order to inhibit corrosion issues, right? Since you put external components, external things, if you do not take them out, they will start accumulating within the system, right? So you have to do blow down to take out, to avoid accumulation of these chemicals, right? So that's also a source of losses, energy loss. And once again, as we saw for the hydrogen plant also, at several occasions we saw it's always a trade-off between capex, opex. So for steam system, it's also a very delicate balance between capex, opex. One example we discussed in the morning, you have steam velocity 25 to 40 meters per second. That's a typical range for your header. Higher the velocity, what will happen? Higher the velocity, higher is the, higher the velocity of steam in the pipe, what will be increase? Higher is the pressure drop. I think you said, somebody said already in another session. So higher the velocity, higher is the pressure drop. And what will happen if we have higher pressure drop, steam lines? More condensation, more losses, right? But high velocity also means you need very small pipe. So you can save on capex.
Area is small. Area is small.
Area is small, but and area is nothing but money, because area times thickness is actually what you pay to your.
I think it's satisfied equation of continuity as well.
Can you elaborate more?
No. Actually, PV, which satisfies equation of continuity. So if we decrease the area, so pressure will increase. When means squeezing pipe.
Yes.
So
area is the flow area, the diameter. Smaller. Yes, exactly. So it's always a trade-off between capex, opex. So far we had a look on how we use steam industrially for heating purposes, thermal energy extraction. And now we'll spend another 5 minutes, 10 minutes on how we use industrially for power production. And so that was the first steam engine, or let's say steam use shown or reported 2000 years ago. And I said earlier, we moved from this very simple thing to supercritical, ultra supercritical, gigawatt scale power plants. Right? So basically what happens is you convert the chemical energy of your fuel to the heat capacity of flue gas. So you transfer heat, chemical energy of fuel to the flue gas as thermal energy or heat capacity, and then transfer this one to steam and expand the steam and extract kinetic energy, move your generator to produce power. And we will not talk about the steam turbine generator in these slides. So earlier for thermal energy expansion, we moved from here to here. We also saw basically if you move from here to here, we can also extract energy. And it's better if we are expanding steam. It's always good to have very high pressure difference between point A and B. or we can also increase the enthalpy by superheating it. Right? So we superheat steam, so that's the superheating. Yeah. So out of 3 different scenarios, we saw that this is the best way. The lowest the pressure here, better it is. Highest the pressure here, better it is. Higher the superheat temperature, better it is. So same example, we have natural gas, we burn it, that's the amount of flue gas. That's the amount of steam we produce at 30 bar for this example. 235 is the situation. Go and turn the turbine of the STG and generate power somewhere around 300 megawatt. But to produce this 3 megawatt, we saw earlier, we need somewhere around 300 or 250 kg per hour of natural gas. But now we need much more because the efficiency here is only 28-29%. And why is that? Because enthalpy of steam coming out of the STG is much higher. It's not totally condensed. In the thermal example, we saw that the enthalpy was much lower here because we already condensed it completely. So once again on the same TQ diagram, you could see that's the steam generation pressure. We already talked about this. If you move this line up, more will be the chimney heat losses, right? So for steam generation, you need high pressure, right? So for power production, if you are burning fuel, you will have a lot of chimney losses theoretically. But in reality, you will not send flue gas at 400, 500 degrees centigrade to chimney, right? Because that will be a big mistake because a lot of energy will be lost. So what do you do normally? You go to the dual steam system. We already talked about this. 30 bar, 6 bar. Another way would be is a lot of energy left here. What we were saying earlier, it will be condensed and energy will be lost to atmosphere, recycled back. But what you can do, you can extract this energy. Right? You condense from vapor fraction 91% to 0 vapor fraction, completely condense it. So generally this will be rejected. We'll see in coming slides. Instead of rejecting it to atmosphere, you can use it for something else. Right? So once again on the same diagram, you see we start from point A, even higher pressures, 80 bar. We increase this. We increase the energy extraction further per kg of steam because we are going even higher with the pressures here. So higher the pressure, we realize with this that amount of energy we can extract is much higher for same amount of natural gas. Similarly, for this amount of power requirement, natural gas requirement will go down. Right? So thereby our efficiency is slightly increased. Right? So we said that's actually the difference what will be translated into power production, right? So first we saw we go higher here on the temperature. Another way to increase this difference would be going lower on the pressure on this side. So instead of 1 bar, now we are coming out at 0.6 bar. That means under vacuum. So 913 or whatever was we had earlier for this point, for this example, now it becomes 1250. So you, for the same amount of steam or same amount of fuel burn, you extract more power. Now suddenly efficiency increased to 37%. Like we applied this energy balance in out for a thermal system, for the power system. Once again, energy in is whatever you burn, our fuel burn. Energy out will be the power out, the electricity you produce. And we have similar energy losses, but one new thing is the final steam condenser. Because we realize we'll always have the steam condensed somewhere, right? Because as you said in the morning also, these turbines cannot accept condensing steam.
So it is a kind of energy balance across multiple units.
Yes, overall. Okay. How we can further increase the efficiency? By having two cycles. First, from the flue gas already, we generate power directly. So earlier what we saw, we burn fuel, and from the hot flue gas we generate steam, and this steam we use to turn the turbines, right? But what else we can do? We can directly turn the turbine using the flue gases. If these flue gases are at high pressure. So in the earlier, let's say, power plant, you simply burn at atmospheric pressure, and then you generate steam at high pressure on the steam side. But here the combustion is at very high pressure, and you already extract a lot of energy. So we already see 2000 kilowatt we already extract. That means flue gas temperature coming out from here will be much lower. And then the remaining energy you extract via steam. So it's kind of combined cycle. It's not just steam, but it's the gas and steam. That's why they call it combined cycle. With this two cycles, you already increase efficiency to almost 43%. And to represent this in this TQ diagram, so that's the flame temperature typically, and you extract energy directly via gas turbine up to a certain point, right? And then you go further. So if you apply process heating, so you could see heat for process use 000, no process heating, all goes to the condenser, right? Efficiency is low. And if you can use this heat for process and no condenser, your efficiency, overall efficiency is somewhere around 90%.
Again, in the last session of today, so what I will do, I will be covering one basic numerical, right? And if we perform that solution, we will able to have the calculations learned what Professor Dr. S.K. Shrivastava has elaborated till now, because he has taken some basics, then arrived at some conclusion. So all those things needs certain calculation, certain stoichiometrical procedure we have to go through and make the calculation. So by solving this problem, we will able to understand each and everything, and we will able to calculate such kind of calculations, right? Yes. So the problem statement is nitric acid is produced in the Ostwald process by the oxidation of ammonia with air. That is what we already know. In the first step of the process, ammonia and air are mixed together and passed over a catalyst at a temperature of 700 degrees centigrade, right? The following reaction takes place. 4 moles of ammonia reacts with 5 moles of oxygen, and we get 6 moles of water and 4 moles of NO. This is the reaction which takes place over the catalyst, right? The gases from this process are passed into towers where they are cooled, and oxidation is completed according to the following theoretical reactions, right? 2NO, okay, which we received from these earlier reactions. 2NO plus O2 gives 2NO2, right? And then this NO2 gets reacted with water, that is 3NO2 plus 2 plus H2O gives us 2HNO3 plus NO, right? And this kind of reactions gives us the nitric acid, right? The NO liberated in the final step, right? The NO liberated in the part reoxidized and forms more nitric acid in successive repetitions of the above reactions. Mouse मेरे पास में आ सकता है? Can I get mouse? Okay. The ammonia and air enters the process at a temperature of 20 degrees centigrade and pressure of 750 mmHg, right? So this is what the conditions of the inlet ammonia and air enters. The air is present in such proportion that the oxygen will be 20% in excess of that theoretically required for complete oxidation of ammonia to nitric acid and water, right? So this is certain statements of the gist of problem is given, right? The gases leave the catalyzer at a pressure of the gases leave the catalyzer at a pressure of 743 mmHg and a temperature of 700 degrees centigrade, right? So what we have to calculate is part A, calculate the volume of air to be used per 100 cubic feet of ammonia entering the process, right? So as I told you, air and ammonia enters in the process. So suppose the ammonia is entering and the volume of that is 100 cubic feet, right? What will be the volume of air to be used? So that is to be calculated. Then part B, calculate the percentage composition by volume of the gases entering the catalyzer, right? So at various stages the process will be. So to the catalyzer, what composition of gases will be entering? So that we need to calculate. And part C, calculate the percentage composition by volume of the gases leaving the catalyzer. Okay, so leaving gases also composition we have to calculate, assuming that the degree of completion of the reaction is 85% and that no other decomposition takes place, right? So this is another statement here it is given. Then part D, calculate the volume of the gases leaving the catalyzer per 100 cubic feet of ammonia entering the process. And in last part, that is in part E, we have to calculate the weight of nitric acid produced per 100 cubic feet of ammonia entering, assuming that 90% of the nitric acid entering the tower is oxidized to nitric acid, right? So as we all know, during the solution of any stoichiometrical problem, we need to define the basis, right? Either 1 gram mole or 1 lb mole, right? Or 100 cubic feet of volume, right? So we need to decide one particular basis, and based on that we have to proceed the solution, right? So here we can take basis as 1 lb mole of ammonia, right? However, it is said that in maximum calculations they have been asked find out certain things if there is 100 cubic feet of ammonia entering in the process, right? So rather than taking the volumetric basis, it is always good to use the lb mole or gram mole as basis, right? So what we will do, we will be assuming 1 lb mole of ammonia entering in the process, right? And then we will find its volume, and accordingly we will be converting the desired answers then, right? If that much of volume is being entering of ammonia, right? If enters 100 cubic feet of volume, then how much will be the compositions and all those things. In that way we will do, right? So now the reactions, the overall reaction is something like this. We have seen the 2 or 3 reactions. If you combine all those, right, we will be landing up with this this first reaction, that is 4 NH3 plus 5O2 gives 6H2O plus 4NO. Then 2NO plus O2 gives 2NO2, 3NO2 plus H2O gives 2HNO3 plus NO, right? So if you do combine all these reactions, it will be landing up with this resultant reactions, right? So NH3 plus 2O2 gives HNO3 plus H2O, right? Now theoretically we can calculate how much oxygen will be required, right? As we decided that our basis is 1 lb mole, by looking at the reactions you can easily tell that 2 lb mole of oxygen is required, right? If we would have taken basis 100 cubic feet of ammonia entering, it would have been difficult for us to get known how much oxygen will be required, right? Because volumetric kind of calculations is not being reflected by virtue of looking at the reaction. But the beauty of our assumption is, okay, by looking at the reaction itself, you can tell that 2 lb mole of oxygen is required theoretically if the 100% conversion of the reaction is, right? Yes, so here oxygen required will be 2 lb mole. Now how much oxygen we need to supply, right? It is stated in the problem statement that 20% we have to give extra, 20% excess, right? So 1.2 you have to multiply, and that much of oxygen we need to supply, right? So 2 lb mole multiplied by 1.2, that is 2.4 lb mole of oxygen we have to supply, right? Again, oxygen generally is not available in the pure form. So wherever oxygen is required in industry, we supply air, right? However, sir told that if you supply the entire air instead of oxygen, okay, so many things, okay, this nitrogen will take away along with that, heat and all other kind of thing, okay, the exhaust gases will be more, right? So we need to handle all those, okay. But for the sake of economical point of view, right, rather than separating oxygen from air and using that, okay, what we do, we supply the air, right? So how much air will be supplied? 2.4 divided by 0.21, okay, because stoichiometrically we assume that air contains 21% of oxygen and remaining 17% of nitrogen, okay, we neglect all other gases, right? So the air to be supplied will be 2.4 divided by 0.2, right? So in that way 11.42 lb mole of air we have to supply, right, as per the resultant reactions we could conclude, right? Yes, so now you can find out volume of this much of air, right? If we have to supply 11.42 lb mole of air, how much volume of air we will be supplying? Because the moment we decide that this much of lb mole of air we have to supply, right, we will not calculating the lb mole available in the some climate, and then we will be using exactly that, okay. What we will be doing, we will be using certain volumetric device, okay, which will be sucking the air and will sending that into that particular process, right? So depending upon the condition of available air, I mean temperature and pressure, right, we will be taking the volume, right? How much volume or how much volumetric flow rate of the air we have to use, so that again we have to calculate, right? Because we need 11.42 lb mole of air, right? If we give more supply, again that issue will be there, that it will be taking away the your heat or your some reactants also, some byproducts will be formed unnecessarily more, so again its separation and all that kind of problem you have to face at the end, right? So it is better to have very precise excess percentage, okay, and very precisely measured supply of either feedstock or the air, right? Yes, so now this 11.42 lb mole of air needs to be converted into volume, right? So at what temperature, at what pressure it is available, you get it identified, okay, and then convert its volume, right? Volume of 11.42 lb mole of air to be supplied, right? So we know the ideal gas law, right? And that you can use, okay, P1 V1 upon N1 T1 equals to P2 V2 upon N2 T2, right? So we know N1, we know N2, okay. Suppose at left hand side, okay, N1 means 1 LB mole of any gas, either air or oxygen or nitrogen, right, occupies how much volume at what temperature and pressure, that we know on left hand side, right? So here you see at 0 degree centigrade temperature, right, means 273 Kelvin temperature, okay, and 760 mmHg of pressure, any gas, okay, any gas, if it is 1 LB mole, will occupy 359 cubic feet of volume, right? I have written the temperature in Kelvin and pressure in mmHg, right? However, you can convert it into PSI, right, in Rankine, and accordingly you can have the calculations here directly on, because on both sides if I use the same unit, no problem, right? Yes, so at 273 Kelvin temperature and 760 mmHg pressure, 1 LB mole of air will occupy 359 cubic feet of volume, that we know, right? If again 1 LB mole of air available at 293, because here it was said that in the problem statement 20 degree centigrade is the temperature and 750 mmHg is the pressure at where the air is available to be supplied, right? So again here you can write directly N2, or then subsequently you can find out this much of N2 will occupy how much volume, right? So same thing, here N2 has been again assumed 1, right? At 293 means 20 degree centigrade temperature, 755 mmHg pressure, how much volume it will be occupying, right? So this calculation will give you 387.85 cubic feet of volume, right? Now how much N2 is there? 11.42, so to be multiplied. So you see here volume of air at 20 degree centigrade temperature and 755 mmHg pressure, which is, you know, the condition of air to be supplied, right, comes out as 4429.727 cubic feet, right? So this much of volume you have to measure, right, and send to the process, so that the stoichiometric requirement including the excess amount of air can be supplied, right? 20% excess exactly multiplied by the air requirement, right? So and you know there are many instruments which can measure the volumetric flow rate, so that much of air you can supply, right? Yes, so now volume of air per 100 cubic feet of ammonia, right? Ammonia volume, right? Ammonia volume was 387.85 cubic feet, right? And air to be supplied, its volume comes out as 4429.27 cubic feet. So now volume of air per 100 cubic feet of ammonia comes out to be 1142 cubic feet, right? Just stoichiometric, what you can say, elementary calculations, right? By elementary calculations you can find out the volume of air per 100 cubic feet of ammonia. So 11.42 cubic feet of air we have to supply, air available at the given condition, right? So such kind of calculations, such kind of, you know, very basic principles like ideal gas law we have to use, and we have to proceed with the calculation, right? So these calculations or similar calculations has been involved to, you know, understand the calculations sir has shown in the previous lectures, right? Yes, now the B part was, this is the answer of part A, right? The answer of part A you can statement was calculate the volume of air to be used per 100 cubic feet of ammonia entering the process. So part A over. Now part B, calculate the percentage composition of volume of gases entering the catalyzer, right? So we will be making some diagram, right? So this is the diagram, okay? Air available and it is coming to the catalyzer, right? The ammonia 100 cubic feet coming to the catalyzer, right? Catalyzer is at 700 degrees centigrade temperature, right? And the reaction occurs there is 4 lb mole of ammonia reacts with 5 mole of oxygen, and it gives us 6 H2O plus 4 NO, right? So this reaction happens here, okay? And then we send all the products and reacted, if it is, okay, to the cooling tower, right? Yes, so we will see the cooling tower part in later stage, okay? Yes, so gases entering the catalyzer, okay? So how much ammonia we fed, how much air we fed, okay? So all we know, we have to summarize that, right? So here we know ammonia we entered 1 lb mole, right? Ammonia we entered 1 lb mole. Oxygen how much? 2.4 lb moles. Along with that, nitrogen also came, right? Because we supplied air. So along with 2.4 lb mole of oxygen, nitrogen also came. So how much nitrogen came? Total was 11 point something, minus 2.4, right? Total air we had calculated, okay? That was air to be supplied 11.42 minus 2.4, that will be nitrogen, okay? So 9 point something, 9.02 lb mole. So in catalyzer, these 3 components are coming, entering, right? 1 lb mole of ammonia, then 2.4 lb mole of oxygen, and nitrogen will be 9.02 lb mole, right? So we know the exact amount, right? We can find out their composition, right? For gaseous system, the mole composition is equals to volume composition, right? So 1 lb mole, 2.4 lb mole of oxygen, and 9.02 lb mole of nitrogen. Sum up, and then to each one you divide it by the total summation, multiplied by 100. It will give you the percentage, right? So you see here 8% of ammonia, then 19.3% of oxygen, and 72.7% will be the nitrogen. Total will be 100%. So this will be the composition of gases entering to the catalyzer, right? So very simple, okay? If any impurity comes, okay, you need to identify that, okay, and you need to quantify that. Accordingly, its percentage also you can calculate, right? For example, the air is containing some CO2, okay, and some other gases, okay. So if have been identified, we have eliminated all those things to remove the complexity, right, to make the problem more simpler, okay. Yeah. So now this was the composition of entering gases, okay. Now we have to find out the composition of leaving gases, right? So what reaction in catalyzer is taking place, that we have to look at. Accordingly, this 1 lb mole of ammonia is entirely converting into the products, or some unreacted remains. All those things we will be talking it out, okay, after the catalyzer, okay. And then its quantity we need to identify, we need to sum it, okay, all those, and again we will be calculating the composition, right? Yeah. So ammonia oxidized, okay, 85% is the conversion in oxidizer. That was given in the problem statement. Okay. Otherwise you can again regain the question statement. Yeah. So 85% is conversion, then ammonia oxidized will be 0.85 lb mole, because 1 lb mole came, oxidized will be 0.85. Okay. And in the exhaust, I mean in the outlet of oxidizer, right, there will be 0.15 lb mole of ammonia, right, 0.15 lb mole of ammonia will be there, right. So ammonia unoxidized will be 0.15 lb mole. Now oxygen we supplied, that is 2.4 lb mole, but how much is consumed and how much will be unused? So unused oxygen will go in the outlet, right? Unused oxygen will go. Yeah. So oxygen consumed will be, you see the reaction stoichiometrically. So 5/4 multiplied by 1 lb mole of ammonia if 100% conversion is, but conversion is 85%, so therefore you have to multiply it by 0.85. So oxygen consumed will be 5/4 multiplied by 0.85, which gives you 1.06 lb mole. So this much of oxygen only got consumed in the catalyzer, right? So 2.4 was supplied, 1.06 has got consumed, remaining will be there in the exhaust, in the outlet, right? So you see here O2 unused, 2.4 minus 1.06 is 1.34 lb mole, right? So oxygen unused is 1.34 lb mole. So you write down then, okay, at the outlet or exhaust of the catalyzer, what will be there? 0.15 lb mole of ammonia, right? Then 1.34 lb mole of unused oxygen, right? And nitrogen will be as it is, right? Along with air, there was nitrogen 9.02 something. How much it was? Yeah. So it will be as it is. Okay. Yes. Again, the reaction occurred and it gave us NO. Right? NO was formed. So how much NO has formed? So you refer the reaction and its stoichiometry, right? So 1 lb mole of ammonia was giving 1 lb mole of NO. Here 0.85 lb mole of ammonia only got converted. So 0.85 lb mole of NO you will be giving, right? So in the outlet again you have to chalk out that 0.85 lb mole of NO is there, right? Then H2 also again that stoichiometrical you have to see 6/4 multiplied by 0.85, okay, because ammonia will be the limiting reactant, right? So everywhere we are taking care of that, right? 6/4 multiplied by 0.85, that is 1.275 lb mole will be the water in the form of vapor, right? So water vapor, then NO formed, O2 unused, right, and ammonia unoxidized, right, and in addition to that the nitrogen as it is, okay. So all those things we will be talking it out. Yeah, gases leaving the catalyzer: ammonia 0.15 lb mole, O2 1.34 lb mole, NO 0.85, H2O 1.275 lb mole, and nitrogen as it is 9.02 lb mole. Okay, so everything, okay, we have summarized, okay, and then you can find out the composition. Molar composition will equals to volume composition for gases, right? So composition of entering gas in previous part and composition of leaving gas in this part we have completed, right? Yes, now everywhere in the latter part, okay, they have asked the answers in terms of 100 cubic feet of ammonia if enters. So at that condition, we know that any gas occupies 359 cubic feet of volume, right? So 3.26 lb mole of gas will occupy how much? So multiplied by simply 359. So 1170 cubic feet, right? So that was asked. Volume of gases leaving the catalyzer at this condition. Yes, 1170 cubic feet was the volume at the special condition, that is standard condition. Now they have asked at this particular condition, so we can convert it, right? Here V1 we know, that is 1170. The conditions already we know, okay? At this condition 743 pressure and 973, 700 means 973 Kelvin temperature, right? So this V2, that is 4270 cubic feet of volume. Okay, so we have calculated that the volume of gases leaving the catalyzer at the given conditions will be 4270 cubic feet. Okay, so that will be our answer. So I believe that you are correlating the things, okay, the physical things happening and how we are using our calculation steps and the basic understanding, right? So in this way we have to proceed with the calculations, right? And in last part, what was asked, calculate the weight of nitric acid produced. Okay, how much nitric acid produced per 100 cubic feet of ammonia entering, means 0.258 lb mole of ammonia entering. Okay, because we have shifted the basic kind of things in between, right? Because molar composition or volumetric compositions, okay, so it is better to have basic in lb mole, right? So accordingly we have done. Then every calculations they were asked in terms of 100 cubic feet of ammonia entering. So accordingly we have shifted, calculated the exact lb mole of ammonia. Same, that is 0.197 lb mole of HNO3 will be forming, right? So is it clear up to this point? Now the weight has been asked. Generally weight used to be either in lb or gram or kg or ton, right? So we have to use its molecular weight of HNO3, that is 63. So multiplied by 0.63, so 12.4 lb of HNO3 will be producing, right? So the problem statement, why I selected, because it is something happening in the industry, right? And similar calculations we need to perform, okay, being an chemical engineer. Okay, how much air to be supplied, okay, how much volumetric flow rate, then okay, in 1 minute this much of volume will go, right? Or per second, accordingly we can set the flow rate, okay, so that exactly or close to that amount of air will be supplied, right? So any questions? Have enjoyed the calculation? Okay, so thank you. I will ask our one of the valued participant, Dr. Kumar Athankar, who is Associate Professor of Chemical Engineering in the Department of Chemical Engineering at IPS Academy, Indore, right? So he will be sharing his certain insights regarding the process calculation. So Dr. Kumar, please.
So there are three mixing points. So first mixing point, then followed by pump, and it pass through the heat exchanger, then pump, and again second mixing point, and it flow towards the reactor. So exactly the reaction takes place over here. Okay. So now our major task is to make a material balance across each of unit. So to solve this kind of problem, how do we approach? Because multiple units are involved over there. So let's take a simple example. Let's take a simple examples. So we have 2 units. Okay, it may be distillation column, it may be extraction column, it may be crystallizer, whatever it can be. So this is the feed 1 and this is feed 2, which is getting mixed at this point. So this is the mixing point. And after mixing of both the feeds, it enters into the unit 1 and some process takes place, some reaction takes place, and after the completion of whole process, product 1 is coming out, and the second stream from unit 1, which is also feed for the unit 2. Okay, and before entering into the unit 2, one also side as a byproduct which is also coming out from the unit 1. So, and this is the feed 3 which is entering into the unit 2. So there are 2 feeds in unit 2. One is from unit 1 and from feed 3. And this is the product 3. So we have product 1, product 2 and product 3 and 3 feed streams. So we need to make a material balance or a component balance across this whole process. Okay. So how do we approach? So first of all, we have to make a overall balance across the complete flow sheet. Okay. So this is a complete flow sheet, and followed by we have to make a hypothetical box across each of unit to understand how much feed is entering and how much product is leaving from that particular unit. Okay. So this is a hypothetical box which represent the complete material balance across the complete process. Okay, and to perform individual material balance, we have to make a separate material balance across each of point. So the second this is the first material balance across the complete flow sheet. The second one is material balance across the mixing point. Okay, because the feed which is flowing in this pipeline, the composition is different. This is the different composition, but after mixing feed 1 and feed 2, the composition of which is entering into the unit 1 will be different, definitely. So that is why we have to make a material balance across this mixing point. Okay. So this is the units. This is the third material balance across unit 1, and this is the fourth one, and this is the last one. Okay. So we have to make a multiple material balance across each of the point where the composition may be changed or maybe the energy may be changed. The same way we have to perform the energy balance across each unit. Okay. So let's take an example of one example which is not specified. It is a very general example. Okay. Okay. So we have a labeled flow chart of continuous steady state. 2 units process is shown below. Each stream contains 2 components. One is A and another one is B, and in different proportion. And we have to calculate the flow rates M1, M2 and M3 along with their compositions. Okay. So this is the flow chart which is provided, and it is a very general problem. It is not a specified problem. It is a very general problem. Okay. So first of all, we have to try to catch what information is provided. Okay. So the information is provided means this process is steady state. If it is a steady state, so of course there is no accumulation. Okay. And one more thing, it is not mentioned over here. There is no generation and there is no consumption. Of course, no steady state. Steady state means no accumulation. Okay. So the next information which is provided in this flow sheet, the unit 1 and unit 2. So for unit 1, this is the input stream having a mass flow rate 100 kg per hour, and the components which is A and B. So 0.5 kg of A per kg of feed is flowing, and second one is 0.5 kg of B is also flowing. Okay. and as a output from unit 1 40 kg per hour is coming out, in which 0.9 kg of A and 0.1 kg of B is coming out. So we have to identify the mass flow rate of M1 which is coming out from the unit 1. Okay. Similarly, the random stream which is getting mixed at this point, we have to which is getting mixed, that is why the composition will change of the M2 stream and which enters into the unit 2. Okay. So from unit 2 there will be two outputs, one is M3 which is also unknown, and the second output is 30 kg per hour, in which 0.6 kg is A and 0.4 kg is B. So first of all we have to make a material balance. So we have to choose the point where all the information is provided. Okay. So what do you think, which point we have to choose? How many points are there across which we have to make a material balance? How many points are there? As I explained in this part, we have multiple points across which we have to perform the material balance. So I'm considering the same example. So how many points are there across which we have to perform material balance? Feed at mixing point before entering into the unit 1, feed sorry, इसे मिक्सिंग नहीं है, गलत बोल दिया, यहाँ पर है मिक्सिंग. हाँ. So first of all we have to make a material balance across the total process. Okay. Because the reason is, if we make a material balance across the unit 1, this information is not available with us. Okay. If we make a material balance across this mixing point, so this is also unknown, this is also unknown, of course this is known. Okay. So it is better to perform material balance across the total unit, because if you perform the material balance across this unit 2, so this is also unknown and this is also unknown, right? Okay. So we have to make a material balance across this total process, and for easier calculation I'm considering the basis which is given flow rates. It is up to you. If you want, you can consider the basis according to your choice, means either 100 kg per hour or maybe 1 kg per hour. It is up to you. Okay. So the information which is not available in this flow sheet, I'm assuming this the A component which is coming out from the unit 1, which is x1, and of course the B, which is the rest of the parts, which is 1 minus x1. Okay. So, and the flow rate is m1 kg per hour. Similarly for this unit 2, m2 kg per hour, and the composition is x2, 1 minus x2. Similarly for m3. Okay. So I'm considering the whole, means I'm making the hypothetical box, which is I can say the boundary. Okay. Now it is very easy to make a material balance across this total unit. So how many streams are coming in and how many streams are going out from the whole process?
3 are coming.
3 are coming and
2 are going.
2 are going. Okay. Are you sure 3 are coming?
2 are coming.
2 are coming. So these are the various different units, like unit 1, mixing point, unit 2, we need to perform the material balance across these units as well. Okay. So the total material balance is, of course, this is a very general equation, which is input, output, and generation, or maybe something consumption equal to accumulation. So because this is steady state, and there is and I'm dealing with non-reactive multiple unit system, okay, which is not reactive. So if it is not reactive system, so generation and consumption will not be there. So this term means the right hand side term and the last two terms will also be get rid of. So these terms will get rid of. Okay, so we have simply input is equal to output. So we have to make a simple material balance across this one. So 100 and plus 30 left hand side and 40 plus 30 and M3. So in this equation only M3 is not available with us. Okay. So with this help, we can calculate the M3, which is 60 kg per hour of product 3, which is coming out from the unit 2. Okay. So followed by we have to make a component balance across the total process, or means total material balance. Okay. So I am considering only component A. Automatically component B will we can calculate. Okay. So the total component balance across the total process. So input is equal to output. So in the input stream, 0.5 kg of A is available. Similarly, in this stream, 0.3 kg is A is available, and the out which is coming out, that is 40. So in 40, this is 0.9 kg is available, and with this 0.6 kg and M3 and X3. So this M3 is known with us, and X3, only the X3 is not available. So it is very easy to calculate the X3, right? Okay. So this is all about the total material balance. Now we have to perform material balance across individual units. Okay. So across unit 1, of course, because at this time we have the information about this input and output stream. Okay. So input, so the 100 kg which is entering as a feed, and 40 kg which is coming out from the unit 1, and the M1 is not available. So we can calculate the M1. Similarly, we can calculate the component of A, which is flowing through the unit 1. Okay. So this is all about the X1, and if X1 means the A, and this is all about the B, which is available after the calculation of X1. Now this information is available, so it is very easy to perform the material balance across this mixing point. Okay, because at this mixing point, this is input stream, this is output stream, and this is also input stream, right? Okay. So the total material balance across the mixing point, which is M1, right, plus 30 and M2. So now M2 is not available with us. M1 we know 60 kg per hour, but M2 is not available. So we can calculate the M2, and similarly we can make a component balance across the mixing point, which is very easy. So this is 0.255 kg of A. So similarly we can calculate the rest of the B. Okay. Now it is very easy to. So in this way we can perform the material balance across each of unit which is available in the process. Okay. So this is all about the material balance across multiple units in non-reactive system and steady state process, right? So I am done. If any questions or any queries, you can ask me freely. Okay. And if you want to attempt, you can attempt this problem. This is also non-reactive multiple units material balance problem. Okay, which is also steady state process. So in this problem statement, we design an acetone recovery system having flow sheet shown. All the concentrations shown, both gases and liquids, are specified in weight percentage to make the calculation simpler. Now we have to calculate the stream A, right? Stream A, which is this one, F, which is coming out from the absorber column, W, which is also entering into the absorber column, B, which is coming out from the distillation column, and the D, which is the output of condenser as a distillate. Okay, so this information is available with us. So the same way as we attempt the last problem, you can attempt this problem, but this information is not available with us. So you have to apply a logic key for which point or for which unit we have to make a material balance first. Okay, so it is very easy to perform material balance across the total unit than for attempt individual units, right? So either you can note down or take a photo, and this is a tutorial problem for you. Okay, so thank you all.